Okay, guys, let us see our screen of today's meeting. This is the August meeting of 2022, and we have a very interesting schedule. A lot of things about FPGA and a lot of things of MECRISP force. And therefore, we have in the first place Ulrich Hoffmann from Hamburg. He will show us demo time MECRISP. So, Ulrich, go ahead, please.
Yeah, thank you very much. So, yeah, actually, the idea of demo time is not to just have talks with slides, but things that Peter Jakacki already started. Now with a formal name, maybe where we say, okay, we want to have demonstrations. And so let's see what we can do. Of course, I have, in some sense, it's an experiment. It's a kind of challenge, show MECRISP to people that already know it. That might be boring. So in German, there is a proverb where you say you can carry oals to Athene, which means you tell people things that they already know anyways. So that could be quite a challenge. And on the other hand, I will probably have something like things that you have in a drawing course. We will learn very simple things. And then I would say something like, well, okay, and now you extend it naturally and you can do painting. Look at Van Gogh's painting, and then you know how the basic principle works. So it's an experiment, and we will see how this turns out. And let me see, here is a camera, and I want to start with this. Here we go, the first problem that we have, it's upside down. This will make me nuts. So let's see, can I mirror the image in an appropriate way? No. Mirror horizontally and mirror vertically is fine. Here we go. So that now it's like I see it on my desk. And so it's a TIVA board from Texas Instruments with an STM32 board in it, and we want to work with MECRISP on that board. And so what we do is actually, let me see. One pitfall is it has two USB drives, sockets, so you have to connect it to the right one. And we do it like this. And let's see, we can connect this board here. And well, at least the power LED goes on. And we want to run MECRISP on it. And so let's see, I had to go to the MECRISP homepage and see what can we do. You search in the internet for MECRISP Stellaris in this case, because that's the one for the ARM chips. And you come to the download section. And then I already did this. You load the latest version of MECRISP Stellaris in this case. And so some people have interest in that. It's a recent version from May. And then you download that, you extract it to an appropriate folder, and then you have an appropriate version of it. So let's see. And well, that's a huge amount of boards that MECRISP runs on. We had this in the preparing chat already. MECRISP is available on a wide range of platforms and boards. And so if you want to do similar things that we do today, just go ahead and download first, look what an appropriate board might be, and then you can go, or you have a board already, check whether MECRISP can actually run on that board. So we have this TIVA board, and it has a TM4C1294 in it. You know this because you can read it. You can read it on the case. Well, and so we go into that directory and we can see what's on there. And Matthias Koch provides binaries, so you don't need to assemble MECRISP for your own board. You can just start with the provided binary and then make first steps. And if you, by chance, at some point in time want to customize it, then Matthias provides all the source code, so you can go and look for an assembler for your platform and then assemble also the core to do it. So if we look at the USB connection, I connected the board to the USB, then we see, there's this luminary micro in-circuit debugger interface. So that's nice. And somehow we need to take the flash, the image, and flash it on the board. And that is, well, a typical stumbling stone, because you need to know how to do it. Often in the README file, you get information on how to do it and read it. In case of this TIVA board, you need to use the tool LM4 Flash, like that. And it's from the LM4 tools project that is available on GitHub. So you have to go take the tools, compile the tools, and then you get the ML4 Flash executable, and you can run it to take the binary image and put it on the board. And we do that. It finds the device that we just saw on the USB port, and it flashes this. So MECRISP also provides, in that case, a terminal. And so let's have a look at the available devices on this Linux system. And we see this TTY ACM0 device. That's the one that is actually the board. We can check this. I unplug the board. I do the LS again. And we see the TTY ACM0 is gone. And LS USB, it doesn't show us the in-circuit debugger anymore. So that's fine. We check again. It's again there. And what Matthias does is he provides a terminal shell script. And let's have a look at that. That one actually iterates from ACM0 to 1, 2, 3, because depending on your computer, the board might show up at some other TTY ACM number. And then once it detects it, it starts up picocom, which is a serial program. If you don't have it in your Linux distribution, use the package manager to install it. It uses picocom to actually connect to the board. And then at the rest of the command line, that's carriage return, line feed, translation, and backspace, delete conversion, and also the command that is used to transfer files to the MECRISP environment, which is ASCII XFAR. It's part of Minicom, I think, and with a line delay of 17 milliseconds. We can discuss this upload issue later on, but anyway, so let's see. We can do terminal, and whoa, we have an OK prompt. That's promising, and I'm pressing the reset button. And it says, yeah, we have MECRISP Solaris here. So that's great. I have to have a look at my cheat sheet. So that's all great. Yeah, we can do some stuff, of course. This is what I normally type in. Okay, the interpreter, the number interpreter seems to work. And then I can say something like countdown. And I'm doing something like 0 do I dot loop. And then I can say countdown. Aha, also the compiler works. So that's great, and control structures are available. So that's a nice thing. So what words are available? And this is a surprise in MECRISP. You get a huge amount of display here. Untypical from the normal list of just the names. Matthias displays the address of the word, the link structure, if it's an immediate word or not, the flags, and also there are information about the code generator that displays there, and the start address of the executable code. Well, that's nice, and so let's see what we can do. Maybe we can access the LEDs, and let's see if we do this. Can we access LED 1? No, we can't. That is because the binary is just a kernel, and then you have to load an extension on top of it to access the board's specific information. And that is something that is called, is available in a file called basisdefinition.txt. And we will go ahead and upload that. Basisdefinitions.txt. Here we go. Yeah, it takes lots of constant definitions for all the port addresses and bits, and does very useful definitions and so on. And in the end, we have a system that is extended now. And let's see. Oh, something is gone. Yeah, I have a setup here where I have a laptop on the where the board is connected, and another laptop that is actually used for. Yeah, did it work? No, it didn't. There we go. Are we there? No, it's still there. So this one is there. So, here we go. Establish the connection again. Here we go. I press reset and we will see what's going. Nice logo, and not just the start line, but so we know the basis definitions are loaded. And let's see what we can do. LED 1. Well, what does it do? It puts a number on the stack. A 2, LED 2. That's actually the bit number of a bit. And if you read basis definition.txt, you learn that it's the bit number on a certain port. And so what we need to do, it's the port N. What we can do is at the address of port N data, we set the LED 1 bit. And a bit set is, what is it? Bit set. Yeah, and wow, the LED goes on. Yep, you saw this. So that's great. And we can also do this with LED port and data big, which is bit clear. If you write things appropriately, then that's great. Port and data big store, and it goes off. Yeah, that's great. In basis definitions, there's also a word LEDs that allows me to press the characters 1, 2, 3, 4 to switch on the individual LEDs. So that's quite nice. Okay, that's great. And I think I need to press escape to get out of this. So, well, that's nice. We can do some nice gambling with it, like flashing. Yeah, we know we all want to do Blinky to check the hardware. So we need to have some kind of delay. The fourth word to do appropriate delays is ms, milliseconds. So let's see. 10 milliseconds should wait for a second and then go on. Oh no, ms is not found. Yeah, the reason is that it's in a file of its own called delay.fs or delay.txt. Here we go. This somehow works with the appropriate hardware of the board in the SOC, and defines word delays, tick, and down there microseconds and milliseconds. So that's great. We need to do in a delay to actually make the configuration of the hardware. And now let's see, 1,000 milliseconds. That's great. That seems to work. So maybe we have a program of our own that we can use. And let's see, I have this Zoom taskbar also in the way. And I need to move it somewhere where it doesn't disturb me too much. Maybe like this. So let's see. We can switch on LEDs and we can switch off LEDs. So let's go ahead and write a small program. Yeah, we toggle LEDs. We saw bits and big store. XOR store takes the value of a bit and reverses it. So we can have toggle LED 1, 2, 3, 4. Clear LED we already saw in principle, and we can clear all LEDs. We have a delay, and then we have a top-level function Cylon, which clears all LEDs and then toggles them in a science fiction way. So let's see. Whoops, we go here, and so let's load Cylon. Here we go. And so let's see, I can say toggle LED 2 or LED 3. And then I can say delay. Let's see what happens. Okay. And then I can do Cylon. And below we see it's a loop. So it repeats this over and over again. We can do this. Yeah, we see the classical Cylon pattern here. And the loop is terminated when I press switch 1. So once the animation is done, I check whether switch 1 is done. And you see there are 2 buttons here, switch 1 and switch 2. And if I press the button, then the loop will terminate. So let's see how it goes. No, that doesn't. Yeah, well, as the forth program does. So the status of the switch is just checked when the pattern has been animated. And if I press the button in between, then I can press it and release it. And at the end of the animation, it's still not pressed. Well, okay. So works as expected, I would say. So let's see. One nice thing about MECRISP is I press reset now, which I do. Here we go. There's MECRISP again. We don't run the Cylon program again. No, it's not there. One nice thing about MECRISP is that it's very easy to extend the program and flash it. Yeah, basis definitions does it in some way. And the nice thing is you can say, if you normally do definitions like I did so far, then they end up in RAM, which is great for testing, experimenting, and interactively trying out and looking what can be done. But if you're convinced everything's fine, then you can go ahead and go ahead and flash it into the flash memory. And you do this by saying compile to flash. And then you just load your program as before. So first delay.txt. Then Cylon. And I do this by hand because that's the easiest way to do. Many people are not satisfied with this. So there's eForce.com and other integrated environments that allow you to simplify all this. But I thought it would be nice to just do it on the basic level so that you get an understanding of what's going on instead of push button things. So here we go. This has been written into Flash so far. Now, if we press the reset button, we want the timer to be initialized. Well, that's not done automatically, so we need to do this. And we also want to start our application. Yeah, and our application is Cylon. And the way that you do this in MECRISP is you define the init word. That's the word that is searched for and executed when MECRISP resets. And how do you do the init? First of all, if there are already initialization, you have to do them first. And then you extend this with your own initialization. And we do init. By the way, this is the reason why redefinitions in forth are like this. This is the pattern that is the reason why words that you define with the same name as already existing word do not change the old definition, but you have a new definition. And that's also the reason why the word name is not findable during its own definition. So this init, the left one, is the new word. This init is the previous one. And now we do things that we did before, and I have to look up that I don't mistype. Init delay. We do init delay to initialize the timer. Then we can do Cylon. And then we can do some, for 2020. I'm back. Whenever I stop the main program by pushing the button. Yeah. So we do this, and it says, well, redefine init. There was already an initialization. And now this also goes into Flash, and I say compile to RAM and can continue testing or whatever. But I also can push the reset button, and let's see what's happening. Let's see. We do it. Yeah, it starts. We see the boot screen, the boot message, but we don't see a prompt. So if I'm pressing enter here, nothing happens. Yeah, but the initialization of the timer has been taken place. Cylon has been invoked, and it's now inside Cylon waiting for the key press of the push button. So I do this, push it, and well, here we go. We get the OK, and the caret returns that I put into the input buffer are processed, and there we are. So yeah, that's nice. I can unplug the board. Serial connection lost. I can replug the board. Here we go. Cylon runs. So that's very nice. And I just in preparing this demonstration, I put out get out some older boards, and there were programs in it. Or also I experimented with block storage on these devices. There were screens on it with notes that I took while presenting this a couple of years ago, and they were still there. So that's quite nice. So no difficult way to do it. You just load the source code with the application. You do the init. And that is how you build up the startup code. We didn't talk about MECRISP, multitasker, interrupt handling, and many other things, the optimizing compiler. So I just want to stop here with the MECRISP startup. So this is from zero to MECRISP application. And you can do this, as we saw in the directory listing. You can do it on with many other boards. So this is a blue pill board, STM F103 or something like this. You look it up yourself, or you take this one, a Raspberry Pi Pico with the RP2040. They both run MECRISP Stellaris, yeah. Peter Yakaki talked about the Pico a lot, putting MECRISP on it and then extending it with Tachyon Force. And well, we did some work because before the Pico was available with a blue pill, and this is this board. It's the so-called Bitkanone board, Bitkanone 2. by Gerald Watney. And as you see, it has a daughter board on it, which is a blue pill. Yeah, and actually there's MECRISP running on that board, and there's an accelerator, that's the small blue one here, and lots of connectors to make these boards stackable. You see the headers to north, south, west, and east. The idea is that you stack them, and on the front side you have an LED matrix. Yeah, and you can control the LEDs in a very similar way to, that I did the LED access in the demonstration before. So let's see what we can do. Either we go with a bare board, or if you want to make a product or hobbyist product, non-profit product out of it, you do a 3D printed case. Yeah, and you stick the board in there. Let's see if we can get this somewhere like this, so you can get the idea. No, it's this way around. Yeah, so you get holes for the headers, and the red button here actually presses the reset button on the blue pill. Yeah, and so I will go ahead and connect this one. There's the connector. Yeah, I'll connect this one, and let's see what's going on, what's happening. So it starts lighting. It has push buttons on the front as well. You see it on the board here, push button 1 and 2, and another one here. And the firmware on it, written entirely with MECRISP, currently works in a way that you do you have applications, and you change the application by going back and forth through the different application. Every application has a logo, and then you use the start button, the left one, to actually start with it. So let's see, this is a demo, or it's mainly demo programs that uses the accelerometer that we have. So if I tilt the bit cannon now, you see I can move it this way, or I can move it this way, and so I can change it in a way that I want. If I want to have a new application, I just go ahead and select some other things. So what is nice, this is forth, colon, semicolon, and let's see what it does. Glowing forth, semicolon, colon, semicolon, and so on. Well, it's just demo. But there's also a LED test. So let's do the LED test. And we see, oops, what's going on there? There's an LED that is out of order. Yeah, it flashes only, but it's way different from the others. So yeah, it's actually the check detects that there is there's an LED that doesn't run as expected. Well, okay, so let's put this down, and I connect to that MECRISP that is on there. And so let's see, we do words and have a look at what's going on. And yeah, what I can say, probably, for example, I can see forth logo, which is the logo of the forth application that we already saw. And Flash actually, so the logo word just writes the image buffer, and Flash actually is not the standard Flash or the common Flash. It just takes the image buffer and puts it on the LEDs. Yeah, and see, forth logo does this, or let's see, rain logo, Flash. Yeah, shows us another logo. And then there is, let me see, what is it? What application? Glitter is very nice. So let's see, glitter logo Flash. We see this one, and we want to run the glitter application. Well, the interface here is that you have to put a number on the stack, which is the state of the application. It's some kind of multitasking that has been implemented here. And we can say glitter run, and then it will display us some things, or 1,000 glitter run and flush, of course, will show us some other things. So let's do that in a loop. Test. Let's see, we put a 0 on top of the stack, and we say begin glitter run flush, and then 1 plus to increment that number, and then maybe we say key question until we press a key, and let's see what's going on there. That looks fine, I think. And let's see how it works. Aha, great. We can run the animation, the glitter animation, and do tests. And we observe this one, and it's only blinking blue, greenish, way different from the other. Also a sign of the malfunction here. Actually, I tried the different colors, and it looks like the red color is actually out of order on that NeoPixel element. Yeah, so that's this. And FitCanon itself is open source, the software. So if you want to look, have a closer look of how it works, then just go ahead and check Gerald's FitCanon. It's a repository. It's actually the MECRISP software that I'm running here, and it's brought up to that board in very much the same way that I demonstrated earlier. So it's uploaded, and it does compile to Flash early in the beginning, and it does compile to RAM and initialization at the end. So let's see. I think, is it that? I think, where is it? Why it could be app.fs. That's actually the runner. I'm not sure if it's the main application. No, not really. Anyway, you can have a look at it, and it's of course the NeoPixels are a little bit more difficult to access than ordinary LEDs. You need to have an appropriate protocol to send the color and the intensity values, but this is done here as well. On the Pico, it would be probably much simpler. You could use programmable I/O for accessing the board, the LEDs. But yeah, well, it's the Blue Pill board on that device. So I'm looking at the watch, and it's roughly half an hour, and maybe we have some time for questions. So thank you very much for listening. And yeah, I'm open for questions.
Amazing, Ulrich. Fantastic.
Thank you, Ulrich. And hey, you know, you inspired me. I spent more time trying to find this board than loading MECRISP on and getting it running. But anyway, thank you.
Sure. Are there any questions?
Okay, while you were talking, Ulrich, I took a few notes. Okay, the first question is, what are the different bin versions? Like when you get the package for MECRISP, you get different bin versions. There is one that is smaller, 16K, another one around 20, another one around 28, I think.
Yeah,
they're called just a bin. Another one has RA before the bin. Another one has RB-RA. What's the difference?
It's different words that have been loaded. There are versions that have an assembler or disassembler already loaded, and others that don't have it. And at the top level, you normally find the leanest one, the smallest one, And then there are also subdirectories in some of the boards where it's called, I think it's pre-built or something like this, where you find extended versions of the image. And to save you time, loading the simple image and then uploading all the devices or the extensions, you can also go for the appropriate pre-compiled or prepared images. So in case of the MECRISP Stellaris, there's just the MECRISP Stellaris TM4C and so on bin, which is the smallest one, and then there's the pre-compiled one, which in the name says MECRISP Stellaris TM4C with disassembler M3. Yeah, so it's the base system plus a loaded disassembler, and you can just use that one. So I would recommend just go with the smallest one and try this, and then once this works, you can try out the other ones. Often in the README you find also information about that.
Okay, now
The excuse me, the RA suffix stands for register allocation.
Yeah, exactly. There are actually two versions or two families of MECRISP implementations. One uses exclusively the stack to have at any time the stack elements on it, that uses the hardware stack. And then there's an RA version that does register allocation and especially on RISC-V, uses the available registers to shuffle the stack elements on it. And there's a fair amount of analysis done so that you access the correct register to get the appropriate stack value. Yeah, but both seems to be mature. So I think for the Pico, there's only an RA version, and that works smoothly as well.
okay, I had another question.
Sure.
The word C, when you use it, you get the assembly listing of the word that was defined.
Yeah.
Is there a way of seeing the definition in forth, at least for the user definition?
Not that I know of. So because it's a native code system, it doesn't compile to threaded code. It compiles to native ARM code in this case, and there is no backlink. And it also optimizes, so it's not even a one-to-one correspondence. So you get a highly optimized machine code, and so if it's your definitions, you have the source code. So then you can go for your source code. And most of the MECRISP kernel is written in assembly. So even the outer interpreter is written in assembly. So and that's the reason why the system is also so fast. So I don't think there is a way to get the source code back.
Okay, so no way to see the definition in forth, even for user.
No. So
okay.
Yeah, that's the same. That's the same with MECRISP, Christian. That's that. You know, it compiles down to assembly code, and so it's frustrating in some ways because I like pure forth because it's one-for-one. You know, dupe swap plus, but in MECRISP it could optimize it to one instruction. I can put a delay in between bits, and it can remove them, etc., and so on.
exactly.
So, yeah.
So it's the optimized work that prevents.
Yeah. And the native code generation. I mean, if you look at other native code generating systems, they never have a decompiler that gives you the source code back.
Well, I think Flash Fort was doing the same thing. Most of them, the AM Fort was doing the same thing.
Yeah, but AM Force is not native code compiling. That's
Yeah.
If you do threaded code, then it's a very easy thing because you more or less have a one-to-one correspondence for source code to the code that is generated.
See, once in a while in the assembly listing, you see a call and a word, the name of a word, but that's about it. Okay, third question. Mine was not working on the 430, is working on the Maple Mini. And most versions that I've tried for the Maple Mini don't have the USB port. They run on RX1, TX1.
Mhm.
Did you try this?
No, I have no experience with the Maple board, but you have the same story currently with the Pico, where MECRISP runs on RxTX of the RP2040 chip, and not on the USB port. Yeah, different from the Blue Pill, which we saw, and different from the TIVA board that use the USB connection for communicating. You have to have a separate serial line to USB converter.
Okay.
Yeah, to access the MECRISP on these kind of boards.
While trying all those bin versions, I finally found one that has a USB built in for the Maple Mini or the Blue
great.
Pill.
Yeah.
So that might be something interesting for Peter Jakacki, because he's working on creating a USB port for
Maple
R8.
Mini has USB, yes, a native USB, but it's not Pico compatible, Christian.
But
they're both M0 CPUs.
yeah, but it's a peripheral chip inside the peripheral unit that is the challenge. That's the challenge. But anyway, it might be interesting to have a look at either the Blue Pill code in MECRISP or to just look at the source code to see how it's structured and what needs to be done. But Peter is probably aware of that anyways.
Okay, so thanks a lot. That's it.
Sure.
I think the Maple Mini has the same chip, the same microcontroller as the Blue Pill, so it would be probably very easy to just copy over the USB driver from the Blue Pill to the Maple Mini and have it run quite quickly.
Yeah, the question is if the USB unit is actually the same. So the core is that's not so important. It's
the same microcontroller, I think. It's both ways. It's a STM32F103.
Ah, okay. Yeah, then probably. Yeah, thanks for the hint. And are there any other questions? Well, thank you very much for listening and following the experiment of doing demo time. And yeah. So
we continue. Then next participant, if he is in the meeting, I saw Willem from Dutch FIC.
Yes. Can you hear me?
Excellent. Go ahead, William, with NOF, a tiny file system for SPI Flash chips.
Yes.
Go ahead.
I have to share the screen, so okay.
And a lot of thanks to Ulrich and Christian Hinze for making those questions, and everyone who participated. It was very, very interesting.
Okay, is it clear? Can you see the sheet?
Yeah, try again.
I have started sharing and I have opened my PDF.
Yeah, so try it again.
Okay, I will try. And then, any better?
Yeah. Yes.
Okay, then I'll start. I'll tell you a little bit of NOF. That is a small file operating system for SPI Flash chips. I had built a button like you see here in the example. That's a brush that you can wear when you go out or promoting yourself, and it shows small animations on screen. And those animations I had to store. So I needed some sort of file system. That's why I designed NOF. I have still another example over here. This is a small Flash programmer. It uses a bootstrap loader mechanism, and it can store files in different formats on the Flash chip using NOF operating system. And it's meant as a portable programmer. It uses a small OLED screen to select the file, and when you press start, it selects the right protocol and goes on flashing your microcontroller. That's the idea behind it. Now you go on. This is the used chip. It's a small SPI Flash chip, and you can get it from about 512 kbyte to about kbit to about 128 megabit, if I say it correct. On my prototype, on this picture, you see the OLED and an SPI Flash chip. That's a 2 megabit version. So there fits on the chip fits 8,192 256 byte sectors. So that's about what you can store on it. And the mechanism can address a maximum of 60 megabyte. That is the 128K 128 megabit chip. So that's where it's targeted on. And about the Flash chip, the reading can be done in bytes. Writing is done in 256 byte sectors, and erasure is done in 4096 byte sectors. So there's quite a difference. And I take the structure of the Flash chip leading for the design of NOF. Now a little bit about the design. I use the first sector for the file entry table. I use this spec for setting off. From 0 on, there are file IDs. From C00, there are the directory IDs. So we have a fit for the files and a dit for the directories. The formats of the file IDs. There are 4 cells for each file. The first cell gives a pointer to where the file is stored, and that pointer is given in sectors of 256 bytes, and it's also used as a file ID. The second one gives the directory hash. That's the directory hash with the complete path to where the file is stored. And the last one is the file hash, and it gives the hash code of the file name. I have done this because I wanted to use the area in the small Flash chips efficiently. Finally, there's the file length, and it's also given in sectors. So the file length of this one is 30 sectors. Now, you see some more files. The second file has a directory hash of 0. That means that it's in the root. Then we have an erased file, all zeros, so quite simple. And we know if it's free when there are all FFs in the cells. The next one are the directory IDs. The directory IDs using 16 bytes record format. The first cell is again a directory hash. You can it's the same that you see in this directory hash table in the file ID record. The second part is a 14 bytes name. And you can see that directory source has a 73CB hash code, and you can find it in that file 0 is stored in that directory. So then you can see a little bit how it works. Then what's the format of a file? The first sector of the file of 4096 bytes. Again, the array sector we use as a minimum format. The first 2 bytes contain the fit, that's the file identifier, and an aux byte where you can give some special information about the file. I use this for movie files, and then it contains the number of frames that a movie has. And finally, the file name of 30 bytes. This file name can be quite long, and the rest is file data. And all other records of the file are behind it. They're always behind each other to keep it simple. Then we have a small explanation of what fit does, the file type. We have 6 file types until now: the Texas Instrument hex file, Intel hex, ASCII, a Forth source file, a picture file, and the general binary files. That's all I use for now. Yes, all zeros. The limits of the system, of this system now, are 384 files and 64 directories. That is quite small, but the flash chips are also quite small, and it's easy to change. When you want to change it, you can say, for example, that not only the first block is for the file, the FAT, but you can say also that the second block is for that too. This is quite easy to change, just 2 constants. Then for the searching mechanism, I use CRC16CCITT for that. And every file name and directory name is converted to a CRC code. And that's done by this little routine. If you want to know more about it, you can see on Project ForthWorks on GitHub. There we have a complete explanation about it. And even Uli is making some background information. Some processors do the same in hardware. For example, the MSP 430 has some chips have hardware CRC. That's quite convenient, but speed is of no importance when you type in a name and search for it on this small disk. You don't need any speed up. Then some small information about built-in functionality. There are a lot of more functions, but I would name a few. To connect an SPI Flash, we can mount it just like in Linux. You can define a new directory. You can choose a directory and show a directory. You can ask the contents of a directory. You can show a tree of all directories in the nesting from the path you are working in. You can view a file, you can include a file, delete all files, and add files. And because this system runs on a small microcontroller, the adding files is a little bit different than you're used to, that we see at the end. Then we come to some small code examples. This is all no forth code, but it's not specifically written for no forth. You can run it anywhere. I wanted to give a small overview of the functions. The curly bracket open FL opens a flash, a command to the flash chip. and I marked those green, and it are specific commands for the internal state machine of the flash chip. For example, you see 3 here, and 3 here commands the flash to go in the read status. You can here see the command 6. The command 6 says to the command there a write command is followed. If you don't give the command 6, it won't write, even if you send a lot of data. And so on. Erase is command 20, then erase the sector with the address that's given on the stack. So now, again, the commands, open the command for the flash chip, define a cfetch command for flash. So this is works just as an ordinary cfetch import, but it's written from the flash chip, and it needs a double address because the flash is quite large, and if you don't have a double address, then you can't address the whole flash. Reading a sector, it's almost the same as reading a byte, again, only but you read here 100 bytes at a time in a small for next loop. If you, before you can read, you need to send the address that is sent here. You need to give the address of a buffer that receives it, and then it's just getting the data. Finally, we close the command. Then we have the write on. This, as we said, it was enabling the write to the flash. Then write the sector is almost the same. You give the command 2, you enable writing, and then you go in a loop and send out data. And finally, you have to wait until the chip says, I'm ready with writing. All the whole sector is written, and you can go on, continue. Now, erasing, as we said, was done in 4K byte sectors. So erase sector is any address within that 4K byte sector is good. First we say write on, then we send the command, the correct command, send the address, and wait until erasure is ready. So you see it's quite easy code. Here we have the two constants that define the fetch sector for the file IDs and the directory IDs. And then we have the main command, that's mount, that enables the SPI, enables some internal data for NOV. And then we go on scan the fit record to initialize it. What this does is it starts at fit, hector fit, and that's 0 here. And then it fetches the data until it finds FF. And then when it's FF, that's the end of the used part of the fit, and it just stores it in the value, except that it does a little check if it was spilled and it overflows, and it initializes to the maximum size it has. Then we do the same with the directory IDs. It's also a scan action. And when you have the directory IDs, we just have to initialize the first 3 sectors that can be used for writing for the next file. And it does that by fetching the address from the last used file name. So it gets that from the file record. We have stored the last 3 location, and because all records are in a fixed format, 16 bytes, it makes it easy to subtract 16 from it, and then address the correct address and calculate where the next 3 location on the disk is. And that's all it does. When there is nothing found, it starts at 10, and that's the first free block on the flash chip. And finally, it enables the directory system by selecting the root directory as a start. And that's all about the small introduction about NOV. I can show some commands here. The first command in green is mount. Now it's enabled. We can use the command there to show the directory structure on that flash chip. When we use tree, it shows all the subdirectories too. And the next one is using the view command. I wanted to use the setup of an OLED screen here, but I made a typo, and then the wrong hash was calculated, so it says file not found. And then a second attempt, I typed it correct, deleting the space, and then it just showed the contents of the file. Now the next one, here we see how files are prepared to send to the disk. Fourth column, and the name behind it becomes the file name in red. So this file is sent to the flash chip, and the 3 semicolons give the end of the file. So this part of the file until the semicolons become the ASCII file, and this is a small include file. Then we can use, when we load it, it loads a complete OLED package with setup, 2 character sets, no, 3 character sets, a graphic character set, and a small AGL demo. Now to add hex files, for example, for the BSL programmer, you do the same. You have here a command that gives the signs for which chip it's dedicated to. So it selects the correct programming protocol. Then we select that an Intel hex file is coming with the name C2X55, and that's an MSP430 FR chip. And then comes the Intel hex code, and this closes on the end record of the Intel hex, and then it's ready. Finally, I want to show you a little bit about how it works in real time. Here we have the contents of the current thing. That's one of my it's my prototype no forth button with animations.
Willem, we just see the slide.
Oh, sorry. Yes, I have to select another screen. Okay. New share. Yes, that's it. Sorry.
Yeah.
Yes.
Mm-hmm.
Ready?
Yeah.
Okay, then we start again. I use a new boot up. That's no forth for the MCV 59X9. That's an FRAM chip. And it initializes it does mount on startup. You can see that too when you use in no forth we use an app factor for that. The app factor is just value, and when we do MC, that does a C on the address on the stack. Here you see the mount routine with first the setup. This has an extra setup for the movie player. And then we can use there because all is done, and we can use tree to see the directory structure. And we can you can select any. One of the things I did do here was to show that using the same name is no problem at all. You see here that the directory extra has a subdirectory trees, which has a subdirectory trees, which has a subdirectory trees. And it also goes correct because you start with the hash code for the root, then you add the directory extra, it gets a new hash code. Then you define in extra directory trees that uses the hash code from extra as a start, and so forth and so forth. So you can go on, and you have no problem at all. And it still is quite small. Here you see a list of picture files. And I wanted to show some other, you can use some regular definitions that you use in DOS or Unix. And okay, so we go back to the root. And now I want to select tools and show you the working. In tools, you see some port files. And I wanted to include one. The disassembler, it's called DES. That's loading the include file. Now we have it in the system. You see the last words, DAS and MDAS. So we can now decompile or disassemble the forth system. That's a small thing about the NOV file system. I wanted to show you one last thing. That is a small. I made a small movie of my demo version of the chip. Here you see the movie playing. That's directly from Flash to the OLED screen. This one I made for a comic book artist. When he goes on promoting his books, he wears this brush. So that's it. Any questions?
Nice. Thank you very much.
I think I'm quite good in the time.
I have a question.
Yes.
Okay, William. Could this SPI file system written in forth be adapted for almost any forth system?
Yes, quite easy.
Okay, because I've been experimenting with one on MECRISP, and maybe I could adapt it. So
yes.
It answers my main question.
And I'm preparing it for the project ForthWorks to place it on there.
Mm-hmm. Nice.
The mount command seems to suggest that hot plug is possible, is it?
Yes, that's possible. The mount command is now written for only one flash chip, but it should be quite easy to adapt it with a command from the stack, so you can use more flash chips.
Yeah, I'm asking because I might be interested in it for compact flash, which is not hot pluggable. So yeah. Anyway, this is a research topic potentially.
Okay. Any other questions?
Some questions?
Okay, then up to the next speaker.
Yeah, thank you very much, Willem.
Yeah.
Well,
it was nice.
Yeah. Yes.
Thank
it
you,
was nice.
William. Very nice.
Great. So yeah, our next speaker will actually be Klaus Kohl. Schöpe. Hello, Klaus. And another demo time. And we will learn about FPGA development. And So and how you do FPGA kernels with forth. And yeah, very curious how you do that.
Wrong monitor.
Yeah, we see already the first slide.
Okay. Then I'm Klaus Schöpe, one of the FIA field application engineer in Central Europe for Arrow, but I'm working with microcontroller side 40 years, and also I worked with forth for for more than 30 years. So during my last presentation, I show a lot of old boards with RTX 2000 or NC 4000 and much more. This time I will talk a little about FPGA boards, especially low-cost boards, and so forth, which I used on it. And I use also some other forth version on it, like MECRISP or the MISC 16 version. Sorry for advertisement, but this is the reason why I'm sitting here in my home office surrounded by nearly 1,000 tools, and I give some of these tools to people who are interested to realize it in forth. That's the reason also why I have some presentation with a little more information about what's inside this low-cost board, which I have here. For example, very cheap boards in an area of 25 to 100 euro, so it's easy to use it. The problem at the moment, most of these boards are not available because of Corona and because of the long delivery time, at the moment in the range of 1 to 2 years. So at the moment, it's very difficult to get any of this board. So be happy if you have any FPGA board at home. The first board I show is MAX 1000. It's based on the MAX 10 with 8 kilo logic elements. And it's really a small board, as you see here, because it's only the MAX 10 on it, then debugger together with the serial interfaces. And then to use bigger programs, there is 8 kilobyte of flash and 8 kilobyte of SRAM, together with some peripheral like 2 buttons. One of this is used for interrupt, 8 LEDs. So you can do a lot because communication is possible with USB to serial converter, which is also inside the debugger. If you look on the block diagram, you see there is a power connector, USB connector, which use a dual channel FTTI chip to communicate with the processor and also to program the processor. Next to it, 8 megabyte of SDRAM, 8 megabyte of flash, MEMS sensor, and so you can do a lot with this board. Sorry, I normally use a development tool from supplier. We discussed it at the beginning of this session, and I have to use it because I have to support customer with these tools. Next to this MAX 1000, there are also a nearly identical board with a Cyclone 10LP. Also with a little more logic elements, a bigger RAM, because if you see the MAX 1000 has only 48 kilobyte of integrated SRAM. So normally you have to use this one if you want to realize a 64 KB system with any processor. But next to it, you can use some multiplier inside to make multiplication very fast. And also there is the same interfaces like 2 buttons, 1 reset, 1 user button, 8 LEDs, and then a lot of pins which are available. This connector is a PMOD connector, which can be used for a lot of peripherals. I show it later. Also the same configuration, and here I do a little advertisement for the all NEOS 2. But at the moment, Intel makes advertisement for the new Nios 5 with integrate a RISC-V processor. But there is a lot of more boards with different cores. The analog MAX has also some MAX 10 inside with a lot of peripherals. Then the Smart Fusion kit has a microchip or microsemi part which has a Cortex M3 inside. So it's easy to realize it with force. And then there is a lot of more boards which is available and coming soon with Cyclone 5 and so on. So there is in very low-cost boards a lot of peripherals, a lot of logic elements and memory available. The cost of this board was at the starting point in the range of 22 euro with some Max 1000 board. But at the moment, I see on, for example, Trend's website, which builds this system in the range of 33. And I think it will be more expensive because Max 10 at the moment is not available. And the long lead time shows it begins 2024, which new chips are available. But there is a lot of more boards which are still available. One of the boards is, for example, this small doubler board, which is here in this area, which comes from an external company which combines SEM D51 together with an ICE kit from Lattice. But for example, for bigger application, there is from Terasic some DE10 nano boards or SoC kit. It's a little bigger, but also very cheap with these features. It includes a Cortex A9, a dual core, and a lot of peripherals. So these both boards are used, for example, for simulation of a lot of old games and so on. So the Mr. family, I show it later. Then, of course, the DE10 light board, you see it here. It's also a very small board, and I show later MECRISP on this board, which is built this year. And then, of course, there are some older boards like the Lattice XP2 and the Pico kit, which is used, for example, from Ting to realize some 8002 fourth version. And also there is some Xilinx board, but the same problems. Papillon is expired, so it's not longer available. And for example, on the Trends website, you see the Zynq board. So there is a lot of boards which in a range of 10 to 100 euro, and it's very good to use. In many cases, you have the problem with the serial interface. So you see it also on the DE10 board. There is no serial interface directly over USB. So you have to use an own USB adapter to get the serial to run. But you have a lot of buttons, switches, hex display, and in many cases you have also additional memory on this board, so you can even run Linux on the bigger board, and on the smaller board you can use any RTOS. If you look on the smaller boards, you see a lot of connectors, for example, the PMOD connector. And there is a lot of adapter boards which is available from Digiland, which can be used for any displays. And also, if you use the other boards, it's Arduino MKR standard. So you can use a cheap adapter to combine it, for example, with a display and so on. So there is a lot of possibilities for the low-cost boards to make your application up to motor control with high-end performance of this FPGA. And we have customer who really use this FPGA for motor control or especially for stepper control, because FPGA are very good to control this lot of interfaces in real time. But there is more. For example, you can realize own processor cores, and in many cases there are websites which are directly usable. For example, 8051, RISC-V, 6502, Z80, and of course older PIC and 6808, or especially AVR, because it's a normal platform for any Arduino kits. But you can also use Forth or Basic or MicroPython accelerator with this FPGA. But my focus is really using, for example, Forth processors on this FPGA. And so you can use, on one side, the standard processor together with FigForth or newer Forth version. And you can also use this FPGA to realize any emulator of this older processor family, like KIN, AIM, C64, and so on. But for me, it was very interesting to see there is a lot of implementation of own Forth processors. So for example, I use also the J1 and modify it for my own version. And there is a complete system available using the J1 basics together with eForth. Also, Mr. Ting used in the past a lot of different FPGA version like the Cyclone 4 or the Lattice XP2 to realize his own Forth version, mostly on microcontroller like 8002 or the 8080, and or the simulation of the PDP-1. So there is a lot of option you can use on different boards, but there is more. For example, Don Golding talk about FP1, so the new Core 1 is shows this year in some presentation and still in work, but there is a lot of older Forth processors from Brad Eckert, Phil Kopman, E. Haskell, and so on. Also, Bernd has his own old B60 Forth processor, and especially if you are relay on old RTX 2000, there is an RTX core available from MPE. After me, Klaus Schleisiek talk again about some microcore, and what I have to show is also the MISC-16 from Steve Thiel, and there was in the past also some other Forth processors from mixed mode, but I don't hear anything after the beginning. And other articles are still available, and there is a lot of concepts still available. So if you look on a website and you search for Forth IP, and then you will find maybe directly the source code for these things in different languages like directly VHDL or other ones. My time with Forth began before more than 30 years. Uli know it. So we start with different Forth version, Volksforth, and so on. And I work for a company who use NC 4000 and the RTX 2000 for own application in measurement systems. So I have to realize an own Forth version, which are running on the Z80 on the PC and then on the RTX 2000. So it was for more than 23 years to start, 32 years to start with it. And also during this time, we was in connection with Zilog. And so I realized Forth version for the Super 8, which is a modified S8 with additional and indirect jumps. And after a long time in 2002, I start with a new own force version with a target to realize one with flash handling, better flash handling as in the past. And it needs again more than nearly 20 years to have something to run. And only beginning at 2020, I do a little more with force. And so I'm starting with J1 force, but I'm not so happy with this one because it was a 60-bit per address force version. And so I don't like it because I'm normally rely on microcontroller, and I don't want to think about handling strings in 16-bit addresses. And so I realized my own small force version for internal RAMs. And after using some Max 1000, I also adapted to the Cyclone 1000. And then I tried different other cores like 6502 and, for example, during the last time RISC-V. And during the last activities, I also start again with the primary concept behind MC-Force because it was also a simulator with a force core which only use 64 different opcodes. And then I realized this on an FPGA. And in parallel, I test the TIL 1802 on the force machine. So during the last 2 years, I do a little more with force after a very long time, which I only use it internal for some smaller things. The difference between the J1 and the K1 is the memory is organized in 8-bit per byte. So it's 32 kilobyte, which is available on the Max 1000. If I use bigger boards like the DE10, then I can realize a 64K flash version. But also I can realize, for example, VGA output. So I have a display external. And so I have to modify the opcode. So J1 use only one at the beginning if you have a 32K value. And then using 13-bit if you realize addresses for jump and call. And then, of course, the last one also 30-bit to realize arithmetic on the processor, which are involving the next and the top of stack and the return stack entry. So you have some features to modify the stack with one word and maybe combining some things. And I modify this because I think it's more interest for a user to have literals in a range of minus to plus 16K. And so I use literal, which are using this bit 14 to expand to bit 15. And I add an additional opcode to invert this bit 14. So you can also realize in 2 commands this full literal area. And I modify also the address for a call to 40-bit because normally you can only jump to a 16-bit address. So you have still 32K call address, which is available. So jumps is reduced to 4K plus minus, but in addition, I have a jump for the for next loop. So I add this one, and the last modification is that I can do arithmetics within memory accesses. And so this is a little modification, so it's not so small if you see on the opcode. So if you see this K1, it has a lot of additional function and opcodes, so you have to do a little more. And this leads to a bigger resource which you need in the range of 4 to 5 kilobyte kilo logic elements. Okay, why small force? Always the same. Normally, I write all my force version in force. And so I have a lot of experience to write assembler, disassembler, and simulator for different processors. And then I'm still a fan of using nearly standard force. So maybe because I begin with Chuck Moore's force version and they are very special. And so I do always my standard force version, and I'm coming from the Volksforce and the F83. And so I try to stay in this area, but especially for FPGA, I use the terminal to download the application and make it run on the processor. And also I hate this big force, big letter things, because in German keyboard, it's difficult to handle. And so I decide to ignore the bigger and lower letter, but I save it. So for example, I use always bigger letter for loops and condition, and I use normally small letters. And especially for this compact small force, it needs only 65K on this force processors, maybe 8K on a normal microcontroller. And I have two words which are used for auto start, for example, this variable tick init. And of course, if there is an error, then it use tick abort to modify the abort routine or error routine. In addition, there is a lot of hardware-specific function, for example, the address for the LEDs, which are used, and 32-bit counter to read the actual time, internal access to PMOD connector, which is only a port, then using serial interface or SPI interface for the accelerator, then looking for the button, key emit as a standard interface, millisecond as a delay routine, and then there is access to the internal flash on the MAX 1000 or the external flash on the Cyclone 10. And then there are two commands. One is save you, the complete save of the actual system, and loading the actual system back to the RAM. And so I can realize with the tick init and with the save U, I can realize the auto start application. And normally this auto start application using the standard force in the MAX 1000. And if he recognizes there's no button pressed, then he loads the application out of the flash. And if I press a button, he uses still the actual force version. And so I can realize any application. And if I see there is something wrong, I press a button and press reset, and then I have my standard force again. I will show it later. So it's now time for a live demonstration. I don't want to show at the moment Quartus except of one thing. Normally you have the development environment, you can compile, you can write it in different languages, and you have tools inside. One is the simulation tool, which I used in the beginning to check all these activities. And then you have the programmer. And this programmer is, for example, used to download the application. And there are two different possibilities to download some application. One is using the SRAM version, so it will be only download and you can test it, but it's not saved in internal or external flash. And the POF version is the complete version, which is normally saved in the application flash. Okay. I begin with a terminal program, and with MECRISP version on the DE10. If I press the reset button, which is both buttons at the same time, it starts with MECRISP eyes. If I see the words, it's a complete forth version. It's very
Klaus,
compact.
can you make your terminal a lot bigger, please?
Yes, of course. Nicht better? Not. Oops. I have to change. Better readable?
Yes, thank you.
Yeah. So you see the standard forth version with all the commands. You see there is also disassembler and debugger integrated. So you can directly use this forth version. So it's one of the forth version. The next version, I have to remove this interfaces and have to add another serial interface, and then I can show, for example, this Max 1000 board, and I have to select the right interfaces. You see, this is a MISC forth, which is from Thiel, and this is also quite a standard forth, very small forth version, and so you have to be careful about what you program. For example, do loop is not available, but you can program. So it's standard forth. It's a second version. The third version, which I can show here, is my own small forth with a K1 on the Cyclone 10LP board. You see, always if I connect the processor, then he changes the serial port. So I can use multiple USB interfaces to realize some application at the same time. And if I press here, the set, then you see it's small forth. You see also some same words which are shown in the presentation, and you can even copy programs and download it. And if you run this example, then you see it's running LED. And at the moment, it's only in RAM. So if you press any button, it's only one, then it stops. And if I use this word and store it to the variable tick init and save this program, then I can press reset. Oh, sorry. Just lost this information. Sorry for it. There's a problem. But I can use the same one with another board. which is a max 1000. The same processor board. And so you can do the same with this board. But what I want to show is what you can do more in this board version. For example, you can download complete application. And for example, I have here, for example, this live program. It's a complete program running live on the terminal. And I can really use this to download. Only problem is you need normally a few milliseconds for the end of the line. That's the reason why I put here 20 millisecond waiting after the start. And if I download this application, you see it runs very fast and makes okay if there is no error. If there is an error, then I wait till this complete download is finished. And then you can start this program, and you see it's really fast. It's only the display which needs a long time because it's 115K serial interface. And I use the same function also, for example, for tests, the commands itself, simple copy, paste. If there is no errors, then it runs through. If there is an error, then it stays on this last line and wait to finish the download. And so it's easy to test each word with only terminal and with a small microcontroller. So I think it's really the smallest environment, only terminal program, maybe editor, and then the program itself. And one of the examples is the last one. It's using the accelerator on this board to show the actual position. So you see the different version. The first line is one axis. The second line is second axis, and then of course the third axis. So it's really easy to using this board, this small FPGA board, together with some interfaces to realize application. For example, this one, maybe you see it, there is an overlay board which using a CO2 sensor for measurement. And so I realized this in forth to get this information and to log this information. And normally my forth on microcontroller are also able to use a special terminal to access a PC file system and to download it directly on the file system. And so you see, if I show the complete Intel area, then you see I use at the moment Quartus Lite. And be careful, if you use newer one, you have to be install also the Windows for Linux. And so I still use 80.1. And then I have different boards, Cyclone 1000, the Max 1000, the DE10 Lite boards. And on this board, I use different versions like the 6502, the K1, my own processor, MECRISP version, for example, and then, of course, RISC-V, a new version. And because this board has also a VGA interface, I can add some graphic. So using low-cost boards can be a lot of fun, but also a lot of work. So I hope you get an impression about my activity using FPGA, forth, and for example, some processor IP to realize some application.
Fantastic, Klaus. Very well.
Thank you.
Thank you very much. So are there any questions for Klaus?
Yes, I do have some questions, Klaus, if I may. The first one is talking about performance. Did you run some kind of benchmark to compare your FPGA-based CPU versus the typical microcontroller-based approach?
It's not really optimized, but at the moment it runs with 50 megahertz, one cycle per opcode.
50 megahertz, 50.
Yes.
Okay.
But I think you can optimize because my first version runs with nearly 100 megahertz. And if you optimize it, maybe more. It's
Okay.
only on this cheap boards. If I use a bigger one, then at least double as fast.
Okay. But of course, it's much more efficient because one opcode, one operation means much more efficiency compared to the traditional approach, right?
Yeah, but during the last time, Cortex-M and the RISC-V has also one opcode per cycle. So it's also very fast, even with the single cycle machines. But especially if you compare it with an older processor like 5201 and or Z80, you'd be much faster with the FPGA. And it's easier to realize this one. And maybe it's also interest for you if you realize FPGA. In some cases, it's better to use on simulator, also written in forth on my side, to recognize any errors in your own forth version because you see it better than on FPGA. But for example, for the K1, I really use a simulator on the Quartus area to debug this core, because it's easier for the hardware side to use a simulator to see is the stack okay, do his right one on the command, especially if you add some function like divide steps and so on. It's not easy to debug in on the hardware. And so I use a simulator to see what's happened. So that's the reason why I also have on Quartus some simulation things like this benchmark, which only use, for example, here a time delay UART interface to set or reset the external pin to show this is a command like punkt to see what's happened.
Yeah, like you would do on the real hardware. And then that's a good transition to my second question, which is because I started using ISC, for example, which is now obsolete, and what is not clear yet for me, maybe I missed that, so forgive me if I missed that in your presentation, is now once you send your VHDL code, right? So once you send the code definition, how do you now adapt the forth implementations? You demoed a couple of them for your new CPU, right? So how do you reprogram, I would say, the low-level words on forth on your new CPU, and how do you store now your total application, your total forth system in a permanent memory?
Normally you include it in some memory because normally you have, for example, here in the Quartus, you have a memory which can be used, internal program memory and maybe more, so stack, for example. There is a program memory, there is a stack memory, and you can define in the design units which are used, for example, because you can use hex code to download it. And if you look on the and use Max 10 K1 board, you have a binary which can be included in this application. This is a hex code for this application. And this will be automatically loaded in the RAM of the processor. And especially the Max 1000 in this application has 256 kilobyte on configuration flash and application flash, and even a little more. And so I use 32 kilobyte for the beginning of the standard force version, but I also use additional 32 kilobyte as a backup for using on save U or load U. So I have a software which only reads from the additional flash to the main memory. Only thing I have to be careful is that the routine itself is on the same address, so nothing has changed during the load.
Okay, so your low-level code is actually part of your VHDL, but by means of an include
yes,
file.
It's the memory part, and you can define this is an initialization memory in what's inside.
Okay, thank you, Klaus.
You're welcome.
Yeah, quick question, Klaus. Are you using any specific Altera primitives, or is it pure Verilog?
This is pure Verilog, so I even write an own serial interface. In this version, there is no images from any application. Maybe the design unit for the ADC converter and for the memory configuration.
Okay, so it should be portable to both Xilinx, Lattice,
yes,
or everything. Very good.
Here is main application Max 1000 K1, and you see there's only a few interfaces like the external 12 megahertz clock, user button, the EB bus. It's connected to the FTTA UART interface, LEDs, P-mode connector, and then interrupt from accelerator and the SPI interface to the accelerator. And this is all what I need from external interfaces, and all other are internal. And I use only the PLL, which is included in the Quartus. And then I use, no, that's all. All other are really done by myself. So UART, SPI, and of course the core. Thanks to A1 as history.
Thank you.
Yeah. Are there any other questions?
Guess what? Christian has questions.
Yeah, sure.
Okay, Klaus, obviously you have a lot of experience with FPGAs.
No, normally not. I started before 2 years because I was asked, can I help people which are using FPGA and NEOS for programming? And I said, of course, because it's no big different to a microcontroller. And so I first start before 2 years with FPGA programming. And so the K1 was really my first contact with this one.
As a beginner, I came up with 3 very basic questions.
Yeah.
What is an FPGA in summary for a beginner? Why should someone choose an FPGA instead of an existing MCU? And the third one would be, is this the way that MCUs are really created?
Partly, if you ask Jacques Moores and not he designed it with block diagrams. No, normally the big difference between a normal microcontroller and an FPGA is that FPGA has a regular structure for memory and then for a logic element. And the logic element exists of a multiplexer, 4-to-1 multiplexer with 16 options behind, which are controlled by the configuration itself. So you can do a lot of function and then a register in the background. I can send you some information about the FPGA and the general concept, but it's PLA, which are regular, and for example, for the Max 1000 in this version, there are 8,000 logic elements which can be used to make some function. For example, you have 4 input for all logic elements and 1 output, and the output can be directly from the multiplexer of this 4, because 4 inputs mean 16 options. And this 16 option can be programmed by the configurator, because you have 60 bits which can be set or reset. And according to this configuration, you can make AND or even ALO out of this logic element. And after this multiplexer, there is a register, because you can save it. You can use it as a temporary one. You can use it as a shift register. And this is 8,000 times available in this FPGA, together with some block RAMs, which can be addressed like a standard RAM, and with multiplier, which can be handled 9 by 9 multiplication. And so you have a lot of resources which can be used internal. And for example, during the last time, you see more and more that multiplier are used for RE application. So you can really use it as for different application, and you can realize different processor, because you can simulate for example, 8051 or 6502. And the advantage for the FPGA is you can modify it, you can expand it, you can add additional register, you can add, for example, multiplication on 6501. So you are very good to add this function. But the better thing on FPGA is you can add any interfaces you need. For example, serial interfaces, UART, even CAN or Ethernet on bigger one, if you have fast enough IOs. So FPGA is very flexible and is used for nearly 50 years on some boards, because as an interface, as a multiplexer and so on. Mm-hmm. What's different to ASIC or to a normal processor. So normal processor is reduced and special adapted to the technology. So it's normally faster and more compact than FPGA, needs less power. And so dedicated processors are still very cheap, very interesting, and often used in application. FPGAs is very expensive in comparison to this one. And especially if you combine it with other functions like analog AD converters, it's a microcontroller has big advantages.
Well, thank you, Klaus. What a great comprehensive summary. And I think that's what we can achieve in the question and answer section. And of course, yeah, you should get in contact and further discuss the questions. You see, Klaus is the expert in that area, and Christian, he can probably provide support.
I think in the picture is my email address, so you can call me directly.
Great.
What I show it again. Yeah.
Right. So, Klaus, thank you again. Thank you very much. And yeah, we stick with the first name, Klaus.
Please unshare, Klaus.
And we stick with the topic of FPGAs. Klaus Schleisiek will talk about microcore and will give us some in-depth view in the VHDL code. That
we need to unshare the screen, Klaus.
There is a button for it.
If you can unshare your screen, please.
No.
Like this.
Okay, yeah. Thank you.
So Klaus Schleisiek, can you share your screen, and then we're very happy to look into the microcore VHDL code.
Oh, this system is slow. Okay.
Yeah, we see it.
Now you should see it.
Yep.
Yeah, hello, this is another Klaus, and I have been working on a forth processor for the past 22 years, and this is now I'm quite happy with the result. And first, let me start with some news, and the most earth-shaking news is microcore now does have byte addressing, because when I realized in IP UDP protocol stack, it became clear to me that, well, it can be done without bytes, but without bytes, I cannot use any libraries and existing code that is around for IT communication. So that convinced me. And the nice thing is I found a solution where you may or may not have bytes, and you may only have bytes if you realize a 16 or 32-bit microcore processor. And if you use other odd sizes, then you have cell addressing. The next thing is, while after doing the addressing, I went through all the old test programs to test the correctness of the processor, and it became clear to me that my division and multiplication routines were not thorough. So then what I did is I prepared a division and multiply test that fits into under 1024 instructions, which means I can get away with a 10-bit microcore to run the tests. And a test for division multiply on 20-bit dividend and 10-bit divisor, and multiplying every number with every other number, or dividing every number by any divisor, takes only 4 hours for a complete test. And actually what I found, that in some cases I got the overflow bit wrong, and now the overflow bit is right even in division. Okay, back to microcore, VHDL code and structure. So you may remember the design flow, and this time we concentrate on this green encircled part, which is the architecture description and the microcore and application interfaces, which are written in VHDL. Again, so you remember it, this is the architecture of microcore. So we basically, we know this machine, this is basically the virtual machine of force. And since microcore is a pure Harvard architecture, so the program memory is completely separated from the data memory. And the advantage of this approach is this is always 8 bits wide, and this can have any word width that you like in the division test, only 10 bits. And now we take a look at the architecture package VHDL, which is, as you see in this picture, the definition of the chip that will be running, and is read both by the VHDL code. So this is the hardware and the cross compiler that compiles for this hardware. Okay, so this is the architecture package file. This is usual VHDL gibberish that you see here. The next version will be 2400, and that will have byte addressing. And then I have a couple of, I would say, compile switches. Compile switches in VHDL don't exist, but you can do ifs with constants. And ifs with constants will be optimized by the synthesizer that makes hardware out of the VHDL code. So it only the code that that applies to the constant as it is set will be synthesized, and the else case will not be synthesized. So there's a difference whether I'm simulating or whether I'm making real hardware. The cold boot thing is, if I press a reset button, do I want to just go back and re-execute the code that is already in RAM, or do I want to call the cold bootloader instead? Then do I have the core or the extended instruction set? Is the FPGA with a multiplier, with a hardware, which means I have a one-cycle multiplier, and which means I have a logarithm single-step instruction. And whether or not it comes with floating point, and whether or not the umbilical interface should have the capability to up or download from the data memory area. So then we define the crystal frequency, how many cycles the crystal frequency is used up by 1/4 instruction, the umbilical data rate for the umbilical link. And then comes the architecture proper, the data width set as 32, exponent width if we have floating point, the data address width, the cache address width. This means the cache is internal data memory inside of the FPGA. And if I have also external memory, then the data address width will be more or less larger than the cache address width. Then I have a constant for the actual cache size, because if the cache address width or the cache size, if I only take the power of 2 of the cache address widths, then this number would have been 4,000, but there may not be enough RAM elements in the FPGA. So I have a second number that says how much of the potential hex 4,000 memory cells are actually populated by RAM cells. And then with the byte addressing, how many bytes are used, or how many address lines are used for byte addressing, and that obviously in the case of a 32-bit architecture is 2 address bits for the bytes. So we have 4 bytes per cell. The register address, which tells me how many internal registers I use, and the registers are located at the far end of memory. So the negative numbers from -1 down to, in this case, 16 would address internal registers. Here we have the start address of external memory. Then we make another constant that makes decisions on the code, whether we have external memory or not. And here we say, well, this is about external memory. I don't want to go into this too much. I have another variable, that constant, that says how large is the program memory and in address bits, and how large is it actually, and how many address bits are needed for the bootloader. So six address bits for the bootloader. This is plenty. And this means this is a large boot program. I think with 6 bits, I can read out a serial flash device and copy the content into the program memory. Then another one constant is the width of a trap width. The address width of a trap vector. With setting at 3, I have 8 instructions available for every trap vector. A trap vector is the reset, the interrupt, the pause, a break instruction for the debugger, and so on. And there may be many more, even soft instructions where you can associate a single byte opcode to a larger force word by associating it with a soft core trap. Then we have the stacks. We have a task address width. That means we have 2 by the power of 3. That means 8 copies of the data in the return stack. So we can use, in a multitasking system, we can use 8 parallel tasks. The address widths of the data stack, the address widths of the return stack. And these are different because the return stack resides in data memory, and now the data memory all of a sudden is byte addressed. So this is actually equivalent to an address width of 2 by the power of 7 cells instead of bytes. So then additional constants that make the life easier later on, that does just some arithmetic on pre-existing data. Then we define the status internal registers, which are some are kind of a priori registers. All you see here in this display, a priori registers, they are always present even in the simplest implementation of microcore. The status register and the single bits of the status register, the data stack pointer, the return stack pointer. Then we have the interrupt and flag register. The nice thing about microcore is you can, with this definition here, that defines the flag and interrupt registers, you automatically say, okay, I underline X bit is an interrupt. And here you see the number of interrupts is 1. And so this is all I have to do to make an interrupt bit. And then we also have a flag register that allows to access additional bits. So this was, the interrupt was bit 0. The data set unit bit is bit 1. This tells me whether an external terminal is connected to the umbilical line. And if so, then the terminal task will be started. And if not, the terminal task will be put to sleep. And the board will do whatever it is programmed to do in a multitasking system. And then for the purpose of testing, we have a semaphore here and a bit out bit that can be read in the VHDL code for simulations to signal the successful end of the force program. We have a version register so that you always know which version you run. We have the debug register that allows to read and write data width wide items from the host computer to the target and from the target to the host computer. Then a timer is an integral part of every microcore installation. So this is our feeling of time. And here I say the timer, it should produce 4 ticks per millisecond, which means a timer tick per 250 microseconds. And then I have an operation on the time register, which is time query. And you have a timeout value on the stack, and then time query compares this against the actual timer, and then you get a flag, true or false, depending on whether the time has elapsed or not. And then lastly, we have control register. That is a register that allows you to set and reset single bits. So, and then we have subtypes, which are common to the entire design, which depend on the registers defined here. And then we have records. This is a big advantage of VHDL versus Verilog. In VHDL, we can define records, and then we only need one signal name to be a UBus port, and then I have all these single data items in one bundle by naming one name and then with a dot identifier. So if I define a signal UBus as UBus port, then I can later on say ubus.reset or ubus.pause and so on. So other records which are used inside the design. Here are special bit combinations for the umbilical loader. And then we have two functions which allow to synchronize the force access to internal registers and the VHDL code. So this function, micro register read, will return a true flag if register, which is an integer address, has been accessed via the fetch or store operator. And so in this case, this function will return true if I access this very register with a read operation and a fetch. And here with the store, I have the equivalent for storing. So that is all that, and that is very flexible. You can use these functions in various VHDL processes to query kind of the use of the external internal register at several places. And then come all the opcodes. This is like a table display. You see how many there are, and how they are kind of logically ordered in the hope that if they are in the right order, then the synthesized result will better as if they are in the wrong order. I don't know whether this is true, but I hope so. And then for every instruction, I just define a constant. And yeah, I don't want to get into semaphores, and that's it. So this kind of defines the complete architecture of MicroCore, and is used in every other file in the MicroCore design. Oops, this is not what I wanted to show. I'm lost. Here we are. So this was the architecture package.vhd. Yeah, the question remains, let me get back. How is this VHDL code interpreted by force? Now, see, I have written this in a special style, like the dash, which usually is the comment till the end of the line operator in VHDL. I have augmented it by a blank. So if I interpret this file using force, then dash just becomes an alias of backslash comment till end of the line. So in that case, both VHDL and force behave the same. Then comes this dash VHDL. Now this is actually a vocabulary, the VHDL vocabulary, and in the force environment, dash VHDL is defined as vocabulary name, and in the VHDL environment, the dash will just be recognized as a comment till the end of the line, and VHDL doesn't see all of this. And then the force code sees dash tilde, and that means skip everything until you see dash tilde dash. So this point is where the forth VHDL interpreter starts to work, and it compiles into the forth environment, cross-compiler, the version number, the constants, the crystal frequency, and so on and so on. All these constant definitions into the forth system, and so the forth system is always synchronized to the VHDL code. And this is a, this is a brief overview. I mean, this is all the code that is needed in the forth, in the cross compiler to do this VHDL interpretation. Here you see vocabulary VHDL, vocabulary dash VHDL, and then the constant depending on what type. Well, I don't want to get into details here, the way I realized this simple interpretation. The backdraw of this simple VHDL interpreter is I cannot port into the forth environment those constant definitions which are the result of an arithmetic expression on the VHDL level. So that is the only drawback. But since all the arguments that go into the expressions are defined before and are simple numbers, I just have to repeat the definition of those constants in forth itself in order to get the same numbers in both versions. So what else is noteworthy? Not really much. You see tick backslash alias dash dash. So this is how this works. The structure of the VHDL code. So we have the architecture package, which are shown. Then there is a functions package, which are functions that are used very often, plus entities that are also very general, like various versions of RAM implementations or ROM implementations or monoflops. Those are all in the functions package. And then here starts the VHDL code itself. The FPGA.vhd is the top level for the FPGA. So this is the file where everything is tied together and where the in and output pins of the FPGA are defined. And if I'm simulating, I'm running this in a test bench on the VHDL level. And the FPGA has a definition of the data memory in microcore, and that may be of a general type, and then it is contained in functions already, or I have to implement a version that is generated by the IP generator, generators of the FPGA vendors, because memories that are not 2 by the power of n large cannot be instantiated as that is the name in VHDL if you define a memory and that will later on really be recognized as a block RAM memory by the synthesizer. So this may also contain IP definitions of the vendors. Then we have perhaps an external SRAM that is also defined here on this level. Then we have microcore itself. The bare bones microcore, as you can see, it does not have data memory, but it already has program memory. And microcore consists of the program memory, the microcontrol, which is the heart of the processor, so to speak. We have a bootloader that runs if you switch on power. And then we have the debugger that feeds through a UART to the umbilical link to the host computer. And a part of the microcontrol is microarithmetic that defines add and multiply primitives which again may be instantiated automatically or for speed reasons or whatnot. You may need to generate the adder, the multiplier with IP kernels of the FPGA vendors. So what I want to do is I want to go a little bit into microcontrol to give you an idea of how the force instructions are realized. And to do this, we go here. First thing I get, this is a large file to give you an overview. This is the microcontrol entity, and this is the definition of its interface to the higher higher levels. What you see here is I use the microbus for those systems which are used throughout the design. So and I just make shorthand definitions of those. I don't want to go into this too much. This is the definitions of all kinds of signals, and then we define the control elements for the data mem, the control signals for the program memory, and then we hand over internal control signals and even registers to the two other levels in the design. So what I want to get into is the internal registers. This definition here, micro register process, is the heart of the whole chip. And so I will, and this here is just reset gibberish. So the actual interesting code is this part. So if the clock enabled signal is true, by way of the clock enabled signal, I can tell the signal the difference in speed between the external clock, which may be much higher as the possible speed of microcore, and only be active every nth clock cycle. So if clock enabled is true, we do something that I don't want to explain. But here we come to the important part. So it may be that from outside the pause signal has been raised. Just for you to remember, a pause signal is, let's say I want to access the UART, but there is no character there. In that case, my UART that I implemented raises a pause signal. And what it does is it sets back the PC, the program counter, to the instruction that failed. So the instruction that raised the pause was a fetch at a certain location, and it wanted to access the UART's data register, and it couldn't do it because there was no data. So it sets back the program counter, it stuffs the operator for the pause instruction into an instruction register, and it also sets a flag that says, well, now do not interpret the next instruction out of program memory, but now you interpret the instruction that is in the instruction register. So the operator for pause will be executed. I'm not going to talk about this, but I'm going talking about the else case. This is kind of, let's say, this is the normal operation if an opcode gets interpreted. And the very important thing here is that R underline in is when on the rising clock edge, and if clock enabled is true, is stored in R. Now, what is R and R in? R and R in are record data types. Here you see them, R and R in. They are of the data type uCore registers, and R and R in contains all the internal registers of microcore. And so, and I have R and Rn, and the reason for that is that comes later on. In a big case statement, the decoder of the instructions is an asynchronous decoder that computes the new state for the registers in the next cycle. So what I do is I define the new Rn that should be valid in the next cycle, and only on that clock instruction I transfer the new values into the actual register set. So there are no registers behind this Rn. It is just internal signals are generated to be fed into the actual register set at this location. So that is the heart of the instruction execution, and the instruction decoding itself, well, starts just here. This is microcore control, and it is dependent on a lot of signals. And here I define more internal variables, which are kind of local, let's call it local variables inside of this microcore control process. And I define a couple of procedures, which is push stack, pop stack, push return stack, pop return stack, well, byte access, that is tricky, and it computes bit patterns from addresses, basically. So we also have word access. If it's a 32-bit system, I have the cell operator, which is a fetch or store. I have the byte operator, which is cfetch or cstore.
Okay, he's gone on my side.
Same here.
So Klaus, your sound is no longer working and your mic is closed.
The video feed is gone too. I think he's
I
disconnected.
have it. I have Klaus looking at his computer, and the video moves. And so let's see.
Right, I'm in screen share.
Ah, the screen share. Yeah.
Unmute. Do you hear me again?
Yeah. Great.
For some reason, I was muted.
So, and now you have to reshare the screen.
I have to reshare the screen. Then I have to get back to the meeting. Here, share screen. Okay.
So, a Zoom glitch.
A Zoom glitch. Okay. Do you see it again?
Yes.
Okay. So what was the last thing you heard?
Was just 20 seconds or something like that. Yeah.
So
you're talking about the bytes add.
Yeah. Okay. So I have been talking byte access, word access. So a couple of procedures, and this is a procedure for a branch. And what is really complicated in a multitasking system? Well, in a single task system, this is easy. Data stack push is data stack pointer +1, and well, NOS DS push. Oh, don't ask me what this is. It is something with RNOS. But it becomes really complicated in a multitasking system, because in a multitasking system, I also have, if in the return stack pointer, I have a fixed part of a fixed address that points into the currently active task. And then I have the actual stack pointer. And so I have written these functions separately in order to always keep the stack itself in a cyclic way, so that it never, one task can never write into another task stack. That's the whole thing here, the important thing. Then we have this toss power of 2 function. This is interesting because it makes the toss power of 2 function automatically makes for a barrel shifter if you use the single cycle multiply, which may be available on the chip. So you have you want to shift, let's say, a number in toss by 3 positions. So you would say 3 shift. And the 3 by this function is then converted into the number 8, and I multiply the toss by 8 and store the least significant part of the result in toss, and that is the shifted result, and that is the single cycle instruction length. So then comes the section where I define default values for the variables and registers. And what you see is the first thing I do, I set the asynchronous RN signals to what the content of the internal registers are, which had been defined in the previous cycle. I define I define defaults for the data stack memory, for the arithmetic, floating point registers, and so on and so on. With the data memory, it's a little bit more complicated because I have to extract, is the address a register? Is it a data cache of internal RAM, or is it external RAM? So these are just functions which I can use later on. And then we start with the actual code. And the first thing is, if it is an interrupt, then I do this. And if it is not an interrupt, then the literal bit may be set in the forth instruction, which means if the most significant bit is set, the remaining 7 bits are a literal or a part of a larger literal. And if the most significant bit is not set, we do not go into this else if case, we go into the else branch, and there are the opcodes. And all the default values which I have set previously in this section, they put the processor into a state where it will execute a no-op. So the code for the no-op is actually no code at all, because it just uses the default values. And then we come, a drop is a pop stack, a dupe is a push stack, a query dupe is, depending on whether RTOS equals 0 or not, we push the stack. So if it is not 0, we push the stack. If it is 0, we don't do anything. Swap over, and so on and so on. And now it goes on and on and on. And so here you see byte addressing makes the memory complicated. But I mean, this solves the complication, and then we are done with it. We have load, character load, word load, store, character store, word store, and so on and so on. What is nice, like for instance, the op local instruction. The return stack is located in the data memory. So you basically have 2 access mechanisms to access the return stack. You can access it as a stack with push and pop, R from to R, as we all know. Or you may access it by direct addressing of the data memory of hardware address. And op local is an instruction that I can say 1 local, and then it gives me the hardware address of the second item. This is why there is a 1, because the first item is a 0. the second item on the return stack, and then I can just do a fetch or store on it. And so with this mechanism, I can build data structures that C programmers love so much on the return stack and actually access them. And then I also have, this is important, a plus store that is quite a bit of code, and it consists of 2 cycles. But what it gives me an uninterruptible plus store, which means I can use plus store to for communication between interrupts and tasks. And I don't have to disable interrupts to do this. This is done implicitly. What else is noteworthy? Oh, not much. Pause. Here is this. You may remember the op pause previously at the beginning of the file, and it is just call a trap instruction, and which trap it is embedded in the instruction itself. So the synthesizer is able to extract that. Then we have unary arithmetic. The M shift, that is an interesting one. I invented M shift as a universal operator to do the shifting, because it takes, let's, for the sake of argument, talk about a 16-bit system. We have a 16-bit number on the stack, and I apply M shift to it, and depending on whether the number of shifts I want to do is positive, then I do a left shift. If it is negative, I do a right shift. So I put away with the R shift and L shift business, because sometimes I have these cases, you have to do computations on the number of shifts you want to do, and the result may be that you need to do a right shift or a left shift. And by having this operator do this automatically on the sign, that is quite feasible. And the result of the shift is you get 2 numbers on the stack. The least significant one is, if you have a left shift, is the left shifted result that you actually need, that is on top. And the bits you have shifted out are then in loss, because you may need them. And if you just do a shift, you do an M shift nip to throw away the bits shifted out, and then you get your result. But if you do, like, for instance, a cryptographic rotate instruction, then you do the M shift and an OR, and you have done a rotate on the bits in a data word. It also exists as an arithmetic instruction, so you always feed the sign bit from the left if you do right shifts. Yeah, and then we have binary arithmetic. I also have special instructions for the to-dupe instruction, because they come kind of for free, and so they are sometimes nice to have, but actually they are not used very often, and so these instructions could actually go. Then there's a primitive for the multiplier if there is no multiplier hardware on the board. Here you see how I use the compiler switches. So I say, if with mult, I just set the multiplicand, I set the multiplier, and then in one cycle I get the product, and I put the most significant part into TOS and the least significant part into NOS. And so that's this part. But if there is no multiplier, I go into this code, and this code is a single step multiply primitive that I have to use as many times as there are bits in my data widths. That it is last. Yeah, the times instruction in forth. The times instruction in forth doesn't check for overflow. So the times instruction is a UN times drop in most forth systems that I know of. And if the result is larger than a single cell, then you have an overflow condition and you get a wrong result in existing forth systems. Not so in microcore. There is this op mult last instruction, and it actually, oops, I changed the code. This is not what I want. It actually takes care of that everything is fine. The toss needs to be all 0. And the most significant bit of NOS needs to be 0, also needs to be 0. I don't even know why the code is written in such a way. But anyways, it computes the overflow bit of the multiply instruction, and the pop stack gets rid of the most significant part of the multiply. And then I get a true overflow. Then we have a division primitive. We have a first division for unsigned division, last instruction for unsigned division. They do special things, cleaning up the stack and setting the parameters correctly. Then we have a signed division step, and here it becomes more complicated because in signed division the overflow is quite complex. And we have the last division step. What you see here in the division itself, it always computes the overflow bit. And if the overflow bit has been set in a previous step, then it will be set always all the way through. So if there was an overflow once, it will carry through all the steps, which is what you want to do. And here in this last step, you see this is the expression in the last signed division step for the overflow. That took me a while to get correctly. Okay, then there is also a square root step, and it does a square root of 2 bits at a time. Then we have flag operations. If we have floating point, we have the fmult, which is it only uses the most significant part of a multiply for fractional multiplication, and that is used in the Horner scheme for computing approximations for mathematical functions. Here we have the logarithm function, we normalize, we make out of 2 numbers on the stack, the mantissa and the exponent, we combine those to a floating point number, and the opposite, given a floating point number, we convert this into 2 numbers on the stack, the mantissa and the exponent. And that's it. This is the instruction decoder of microcore. Okay. I talked about 2-cycle instructions like plus store. Plus store, there are other things that are 2-cycle instructions like the fetch or the cfetch. That has to do with the way that the internal memory, data memory in the FPGA works, because the block RAM cells, as they are called, they have an address register at the very input. And the first thing you have to do is you have to latch the address that you want to access in the address register, and only in the next cycle you can read the content. So this is the 2-cycle instruction, whereas the store is a 1-cycle instruction because you can set the address register and the data register for stores at the same time. And so there are other things. In the case of the if, for instance, this is a 2-cycle instruction because you may remember my presentation on the structure of microcore. The offset to the target for the branch offset is preceding the conditional branch instruction itself. So the if has first, it has to drop the target address from the stack. And secondly, it also has to drop the flag. And this is why this is 2 cycles. And the if does this automatically and always. In the first cycle, the branch address is dropped. In the second cycle, the flag is dropped itself as well. So these are examples for instantiations. I have ported microcore to Xilinx XC2S, to Lattice XP2, Altera EP2, Actel Microsaming A3PE, and the code is now written entirely in VHDL 93, so you can also use it on legacy design environments for old boards. And the reference instantiations I have been doing on a very simple board with the Lattice LF XP2-8. And so these are speeds and resource uses for different instantiations. If I have a 16-bit word width, I use up 988 slices, as these things are called by Lattice. So a slice is 2 flip-flops and 2 4-input logic generators. So 988. Data memory is 6K, program memory is 8K, and the maximum clock is 33 megahertz. The extended instruction set for 16-bit uses 1199, and so on and so on. And you see the resource usage increases with, of course, with the increase of the data width, because most internal microcore registers are data widths worldwide. And so that the change of the word widths directly translate into a change of resources needed. Yeah, that's basically it. Microcore is available on Git. So the name is microcore-VHDL on GitHub. And at this address, you find the documentation on microcore. That's it.
Yeah, thank you very much.
How do I get out of screen sharing again?
Already done.
Ah, already done. Good.
And are there any questions? Okay, doesn't seem to
I have a question.
Yeah, sure.
Why do you use dedicated multiplier for doing bit shifts, when bit shifts can generally be done in hardware using much simpler functionality than a multiplier?
Yeah, but not a barrel shifter. I mean, if you do a barrel shifter, this is a grave of multiplexers. A barrel shifter is very large. And so this was an idea at one FOSS conference by Anton Ertel. He asked, why don't you just use the hardware multiplier to do the shifting? And this number to exponential function, which is hardwired now in microcore, gives me the proper multiplier to do that. And this is much more efficient compared to a classical barrel shift implementation.
Reasonable. Other questions? Well,
Yes, Christian has one question.
sure.
I'd like to know if at least I got the essential of this presentation. What I understand out of it is that we get all kind of details on how to use VHDL to create a micro-core CPU that runs forth.
Right.
That's it?
That's it, yeah. I mean, my presentation is the fourth presentation, I believe, or the third presentation in a series. So there are many topics that I didn't touch on because I have talked about them in the past 4 months already.
So if someone would like to create micro-core, he goes on Git, gets the VHDL code, runs it, and he gets micro-core.
Exactly, and it also comes with a cross compiler and everything you need to run microcore. And I'm quite proud that I have written so much documentation, which you will see if you go to the documentation directory, which is unusual for GitHub projects, as
I do think that you gave us all kind of tricks that are way beyond my understanding now, but that would be very useful for whoever is creating forth CPUs with VHDL. So thanks a lot.
Thank you. Okay, you are all overwhelmed and applications of microcore, and why do you want to have a force processor in an FPGA? Well, it's very simple. If you have complex instruments, let's call it instruments, complex instruments which cannot be controlled by a simple microcontroller, because it also needs an FPGA to interact with complex I/O chips, DACs, and whatnot. Then you need an FPGA in the design anyway. And then it doesn't make sense anymore to have a separate CPU chip, because you can put the CPU in the memory into the FPGA itself. And so you save yourself in the design one entire chip with a lot of pins that need to be routed. So that is, from my perspective, one of the big advantages. And the second, even more important advantage, if there is a bug in the microcore design, I can correct it, or everybody who uses the microcore code can correct it because the source code is available. And there is hardly any processor, at least if it is issued for the first time, that comes without bugs.
For sure.
There's the question of the cost of the development toolchain for any FPGA.
Yeah, I have just used from Lattice. I just have used the public license that you get free of charge. And I mean, on all FPGAs that I had in the list, where it has been Xilinx, Altera, Lattice, Microsemi, I have always worked with the free of cost toolchains, and that was sufficient.
Yeah, I recently took a look at the simulator for the Quintus suites, Altera Intel. The zip files were so big that an HTTP timed out after an hour. I mean, they supply it under the form of 4 GB zip files. It's just insane. But it's nothing to do with
the
you.
other vendors are not much better. So you need a good internet connection, indeed.
Yeah, you need fiber, is what you're telling me.
Now I have downloaded these things even before I had fiber. So if you have 1, 2, or 3 megabit connection, that is sufficient. I mean, it takes a while overnight.
Yeah, I don't. So that's out of the picture. Anyway, I found the complexity of this implementation way superior to something you would code in assembly language, because you have to be so intimate with the hardware. Essentially, what you're doing is you're designing your own architecture, and that takes a hardware-oriented person to do that. I'm surprised that the previous speaker said it took him 2 years to master Verilog. The guy's really good. It's impressive.
No, I started
the same thing is true for VHDL, and as I said, I have designed microcore over a period of 20 years, and it went through several metamorphoses where I mean kind of changed it dramatically. But what I did, I always kept the cross compiler in step so that you would always be able to load the same source code, even though microcore changed dramatically.
Mm-hmm. Thank you.
Right. Are there additional questions? Oh, Klaus, thank you very much indeed.
Okay, thank you for listening.
And our next speaker is Francois, and he made some porting experiences. He had some porting experiences when porting to 479, I think, from other dialects. Francois, you want to share your findings with us. So, tricks and hints when porting source code. So let's see what you have. So you have to unmute now, and you can share your screen if you have anything significant to show. Yeah, probably.
Yeah, my system is a little bit unresponsive. It must be Firefox. After a 3-hour session is becoming a bit crowded.
We will see.
So how do I share now? I'm probably not in the wrong view. Excuse me for the technical problems. Do I have the power to? I don't share screen.
Yeah.
All right. I found it, but the system is extremely unresponsive, even with 7 GB of memory. All right.
I cannot
Here we are.
see your screen, or at least something black, but it will show up. Yeah,
eventually,
here we go.
All right. So the topic of porting forth code, it's mostly esoteric and of little interest to most people. I am a Forth implementer, and back in '84, I implemented a native Forth based on the 79 standard, or at least my understanding of it, for the Z80. This stood the test of time in the form of a printout conserved in a safe place. So 35 years later, I ported it to the 6309 processor which is an evolution of the 6809 by Motorola. And now it's fairly complete. It has some deficiency, but it's very compact. It supports it has a 200-word dictionary to begin with, and the need for porting codes came from the lack of examples, essentially. As far as examples are concerned, I have a number of benchmarks. I have examples contributed by various people. Michel Jean, Bernd Paysan, that's recent. Matthias Koch, this is me. This is Bill Ragsdale. And there's the code from Dimitri Penado, which I like because it's straight forth-kernel code with no hardware dependency. It's oriented towards language interpretation. It's fantastic stuff. But my first experience with porting ANSI codes to my platform was Paul Binet's implementation of the Game of Life. And that was really difficult. It took me 3 months to get it right, but there were a number of lessons learned from it. I didn't support backslash as a marker for comments initially. I didn't support ribbon and a number of things that are ANSI out of the box. So 3 months for the Game of Life, and yeah, growing pains actually. After that, I moved on to implement more and ANSI supporting primitives, obviously. And recently, I went a bit further with Dimitri Penado's code. Yeah, he does prologue in forth. And he does a simple forth expert system. So we'll go through 2 of these example programs, which is the expert system, and Meta 2, which yeah, it's here. All right. So essentially, when you're porting code, you're extending your basic forth vocabulary to provide an artificial environment that would suit the program you're porting. This is what we do here. So this is the expert system written for forth-kernel. It relies on this essential word. This is the only implementation dependent thing it depends on. But essentially what this word does is a reverse lookup in the dictionary based on the value returns by a created word. It returns context string that is the named field for the old timer. So this is what this does, and we're going to run it. This is going to be practical, not really conceptual. Huh? The concepts are the matrices. So here there's a little extra complication because there are different compiling options for the system. There's a reliability option that adds an extra word to every dictionary headers entry. So this is the implementation for a reverse lookup the forth-kernel way. Then we have other adaptations to provide to the system, but they're minor, they're really trivial. One of the important differences between ANSI and 79 is that the value of true in ANSI is -1, whereas the value of true in 79 is 1. And sometimes people use this logical, these flags values and apply to them logical operators with addresses and assume things from the environment. So assumptions is the mother of all fuck-ups, as we all know. So the expert system is after the adaptation layer, you can run essentially the MECRISP code for the expert system as it was intended. So this was the kernel. Now there's the facts section. It will ask questions and try to guess what their disease is. It could be COVID-19, Delta, Omicron, or a common cold. This is all done in cut and paste, although I could load the thing from Compact Flash storage because I've blockified this, but I think it's more interesting to see it like it is. So we can it's always good to have test patterns, I think, in your code for individual primitives. This is something I learned from Paul Bennett. You should always have some test code in your code. So here we see that when we invoke the created words, slow build of symptoms, and this fourth ring primitive, we get the expected results. We get access to the name field. So that's really cool. Now we can try to run the application and actually solve the case. Yeah. Oops. It didn't take any answer for the headaches. Cough. Yes, let's say I'm coughing. Fatigue. Tiredness. I don't understand the distinction between fatigue and tiredness, but if Dimitri was on the call, he probably would be able to. Congestion, no. Runny nose. Oh, that's a yes. Okay. The system was not able to answer this one, but it is. When all the rules are matched properly, let's do another run. Yeah. Quick one. Let's match everything for Omicron. Oh no. All right, let's skip it. This worked so well in rehearsal, believe me, but there are some states situations, so I would like to rerun the whole thing, and I don't want to go there. Trust me, this works. We are going to go to the second example, which is more complex, because initially it required file system support and also extended primitives like defer, is, and call and no name. Meta2 is a compiler generator. Again, the concept is Dimitri Pianado's, and I'm really sorry he's not on the call. Again, an adaptation layer with basic ANSI primitive, which are easy to implement even in a 200 words dictionary. No name is a bit custom and experimental. It doesn't really support errors as it is because it's application level based. Then there was a problem that the original code was based on a file access option, which is optional in ANSI, but still. So I had to convert this into block access. which is easy to do because the access is strictly sequential. Here we begin application level code. So I can do big chunks of cut and paste. This compiler, what it does in essence is it takes language grammar specification as an input and generates a compiler for it. It uses Forth as an intermediary language. This is all the MECRISP code with some fixes. All right. It's very simple code. No machine dependencies, fairly standard. What I did is instead of having the grammar stored in a file, I have it stored in blocks 600 to 602. It's stored under the Backus-Knorr form. Yeah, standard grammar stuff. For people who know this book, this is no surprise. And then we can exert the newly defined primitive like defer, is, and no name. This is still the MECRISP code. Straight cut and paste. No line changes. I should probably show you the grammar specification as a text file. So this is what is stored in blocks, and it is actually the grammar specification for the target language, which is a variant of August 60. But again, the whole concept part is entirely in images. Now we're going to run this. So we're going to run the compiler generator on this grammar specification and see what comes up. So first we load the grammar, blocks 600 to 602, and then we generate a parser for it. It's a bunch of code, which I will cut and paste to show you that this is no joke. All right, here we are. So we are now in a position to run a sample program expressed in the target language, which is this thing. So this is August 60, and it's a bit weird in the sense that the assignments are done from left to right. It's nice for Forth, obviously. So now we're gonna apply the generated compiler to this code. And this is the generated forth code, so intermediary code. Oh, if I miss the variable here, I'll be in trouble. All right, so now we can run the target program. And it does exactly what it's supposed to be and what it does in the MECRISP presentation. I think it was in May last year. And the actual code is this. And of course, people like Christian Heinzer are going to be upset because this is assembly code. But the target forth generates machine instructions just like MECRISP. So yeah, that's what you see. But you see, it calls dictionary words like 0, x is variable, store, x, fetch. This is a literal that is unknown, 1e, okay. It pushes to data stack, and it's all understandable, natural. So yeah, that's my conclusion. Rules to get by when you port forth code. I think this is essential. In my distribution, I include guidelines on how to port ANSI forth to an integrated implementation. But I am not so far from being ANSI compliant. I did an inventory today to be able to achieve the bare ANSI minimum, the core instruction, the core word set. This would have to be done, but there are things like leave, which have a very specific semantics, and although you can have multiple does in a word in the ANSI standard, which is a bit odd. But other than that, this is all. I could make this 79 ANSI compliant easily. I would have liked to show you some of the guidelines, but I'll give you the lowdown on it. The biggest obstacles are environmental dependencies. That if the program you're porting assumes a specific cell size, some byte ordering, or a given value for true, then you have a problem. You have to take care of that. Then you have the case of identical words with different semantics. This is bad. Find in ANSI forth has nothing to do with find with in 79 standards.
Francois, we are out of time, and we need to continue with the next presentation.
I know. I'm almost done. Then you have the featured vector. Yeah, fights versus block. That can be a problem. And then you have non-standard words. So those are the points you need to pay attention to. And I'm done. Right there. If you guys have questions, I'd be happy to take them. I have more to show because when you have defined no name, the world is your oyster essentially. I just wanted to give those porting guidelines, and they are defined on GitHub in Z79 forth repository. That's it. I can stop right there.
Okay, so right, thank you very much. Other questions for Francois? Do you intend to publish your list of guidelines somewhere?
I might if somebody shows interest, but you know, according to every implementation is different. The guidelines stand. I mean, the byte ordering, the cell size, things like this. Maybe in fifth dimension.
Yeah, could be, sure. Yeah, good idea.
Otherwise, they are available on GitHub.
Okay, yeah, thank you very much again. And Brad is eager to show his sockets in ESP32 forth. So without further ado, please, Brad, take the mic and the screen and tell us what you want to show. So very soft on my end. I barely can hear you.
Let's try that. Is that any better?
Better.
All right. All right. So I will give a brief introduction to ESP32 forth sockets for those of you that are working on networked applications. So sockets are really Berkeley sockets, BSD sockets. They're sort of the API for networking on the internet. They date back to 1983, and in '89 they sort of freed up for general use. The key abstraction is a file descriptor as a network endpoint. You can actually use a bunch of the POSIX APIs directly on them, writes and closes and so on. They're multi-protocol and multi-transport, which we'll talk about in a sec, and they're designed to support concurrency, because when you've got network connections, you may have multiple things happening at once, different parties connecting to you, packets coming in, messages going out. It's multi-transport in the sense that it's an API designed to support many different kinds of networking through a single interface. The two main ones that are relevant to us, really the only one that we're going to talk about in this presentation is IPv4, but IPv6 is supported. You can do what's called a domain socket, where it's local to the device, and there are some others. ESP32 actually does support either IPv4 or IPv6. Simplicity, I'm going to focus on IPv4, but the bindings are there. Support has not been fully vetted with the ESP32 forth bindings, but it's likely very close. There are two kinds of protocols that are relevant to us, TCP and UDP, and I'll talk about each of them in turn. TCP is a bidirectional protocol, so you can have a stream of bytes going from one point to another. It's in both directions. It's connection oriented. You have to explicitly establish a connection. That connection can continue for some time and then is broken by one party or the other. And it's designed to allow for multiple inbound connections. So if you have a port open on a particular device, you can have several parties connect to it. Each one of those basically creates an additional socket that lets you handle that communication on a separate channel. It has reliable delivery, and as we'll see when we talk about UDP in a second, that delivery is sort of built on top of another layer of the internet, which is unreliable. And this makes it useful for all sorts of purposes. That, you know, the comment that people use is that it's used for even, you know, communicating with TCP to a probe on Mars, because the connection is able to be robust in the face of changing network conditions and can kind of dynamically adapt to whether packets underneath it are getting through. It's used for a bunch of different purposes, used for web connections, used for SSH, anywhere that you need all of the bytes to make it to the other side reliably and in the right order, and so on. UDP, in contrast, is just taking the internet protocol and sort of surfacing it to users directly. It supports in principle, packets up to 64K are a little bit above. But in practice, especially if you're traversing the internet, you want to keep your packets small because routers in between will actually divide up a larger packet, try to reassemble it. And as we'll see in a second, that is unreliable. It's connectionless. So you're sending individual messages and to an endpoint, and they can be coming in from multiple parties, and then you can be sending out to multiple parties at the same time. So any notion of a connection that you have is something that you build up yourself. The transport is unreliable, so packets can be lost, they can be corrupted, you can get multiple copies of the same packet, and they can arrive out of order. So you have to be careful when you use it to take this into account. If you care about reliability, you're going to have to build your own mechanisms to cope with corruption, to cope with out of order. On some networks, like over a cellular network, there are slightly different properties, like some cellular networks will deliver UDP reliably, but you can still get repeated packets and out of order, so things to be aware of. UDP is used for all sorts of things. This Zoom call is likely using UDP because it's excellent for video and audio applications where you have a stream of data going, and if you fall behind, if you've got a series of images coming to you to display your video feed, if some of them get lost and they arrive later or they arrive damaged, it's better to just drop the frame and move on. And more importantly, you can also have a little bit more direct control over the flow of packets and sort of be involved in sending them more quickly or more slowly, depending on conditions. And for something like audio or video, where the format can be adapted and be more or less lossy, depending on conditions, it can also be a good fit. It's also used for a bunch of low-level parts of actually setting up the internet and setting up devices. So DNS for figuring out the relationship between a domain name and an IP address, or for DHCP to actually assign IP addresses to individual devices. As we do sockets in Forth, we're going to need to know about the low-level structure of that's used in memory by this API. A structure called a sock adder in, which is in is for short for internet, and in particular, this is IPv4, is used to represent addresses in memory for IPv4. There's a family which is typically just the internet family, and then the port, and then the address, and then there's a bunch of unused bytes. A huge gotcha, and this is if you're comparing the ESP32 Forth implementation versus the micro eForth equivalents on Windows and Linux, that you'll run into is that ESP32 uses a slightly more unusual variant of this structure. So where typically you just have the family, the port, and the address, there's also a field for the size of the structure embedded, and the size is typically 16 bytes for all the different address families that are supported. What's going on here is that in the C structure that's used, this is sort of what you would typically see in Unix, but on ESP32, the length is there. And if you don't have that 16 in there, things will behave oddly. So fortunately, as it'll show in a moment, that gets handled by a bunch of the code that's built in. So this is an IPv, oh, that's labeled wrong. This is IPv6. It's got more fields, not relevant. A thing to be aware of with all these fields is that because these protocols were designed, these protocols use big endian throughout. And so in C, you'd be converting back and forth using these macros. In Forth, I've just done it explicitly and coped with them being big endian as needed. So there is a defining word, sock adder, that will create a sock adder, and it pre-populates it with the INET family type, and then you can set the IPv4 address and the port explicitly. With IP address, it keeps it in big endian form in the word that you hold in. With the port, it is converted so that you can print it appropriately. So when you want to make a TCP connection, there's a set of things you need to do. You need to, first of all, take whatever host name that you want to connect to. You then get out the IP address. You need to create a socket of the appropriate type. You need to create a connection, and then you can send data back and forth. So these are sort of the steps that we're going to have to follow to do this in forth. The first step is, of course, extracting the IP address from, or figuring out the relationship between a domain name and an IP address. There's this big C structure that's what's used underneath if you call the get host by name function. This supports the idea that for a single host name, there can actually be multiple different aliases, and you can actually get back both an IPv4 and an IPv6 address. Typically, we only actually care about that last defined at the bottom, the H adder. And so this is how you can do it on ESP32 forth. You pass in a null terminated string to get host by name, and I've just stored this away into a constant. That's the address of that structure, and then you can use this -h adder to get out the address, and you can print it and find out the address of a domain name. Then you need to use sock adder and initialize which port, and then copy over the address that you want to use. So this would be to reach out to google.com on port 80. You then can create a socket, passing in again the family, the fact that a sock stream to indicate that we want a TCP stream, 0 for flags, and then call socket and store that away in a value. And then you connect to it simply by using that socket, using that address, calling connect. And now you've established a connection represented by sock to Google. You can then send messages using either write file, or you can actually use send. Either one works. You'll notice in actually much of the code for a long time, I didn't have bindings for send and receive. There are bindings for them in the latest version now, but you can also use read and write for most purposes, although if you need to pass additional flags, that's where you end up wanting to use send and receive. And here I've got some roundabout words to send over a carriage return line feed, which probably could be factored differently, but I threw this together a day ago. And then you can read the response using read file. And to give you some idea what this looks like, I'm going to actually, I guess we could do it in an actual ESP32. So I'll bring up, I'll bring up PuTTY. Oops, I got to actually plug in the ESP32. So I'll hold it up now. I've just got a board attached, and I'm going to run a copy of PuTTY and connect over the serial port to it. And so I've gathered all the steps into a piece of code. And actually, this will give me a chance to show off one other thing that's hot off the presses. I've now added a visual editor into the system, and you can pull up a file that I've stored there ahead of time that has those same steps that I was showing before. I will exit out of that and go ahead and include it. And this is just grabbing the first, oops, that did not work. Oh, that did not work because I did not set up my my network connection. I've got a block stored that has my my Wi-Fi passwords. You need to do Z, your network name and login to establish a connection. And then I am going to include that same file, and it pulls out the response from Google, which is a bunch of headers, and then also a bunch of HTML or the start of it. So that's demo one. If you want to see an example of a TCP server, the web server that's built into ESP32 forth is probably a good example. The process is sort of symmetric to the other one. You need to create a socket, bind that socket to a local port that you've created an address for. You call listen to specify the number of different connections that you want to allow simultaneously, and then you call accept to get the socket for an inbound connection. You can then send and receive data as before, and then close the connection. There are some challenges with doing servers well. You'll notice that tasks are used heavily inside of the web server, and this is because if you have the possibility of a connection and other connections coming in, you need to be able to potentially be coping with multiple things at a time, and blocking becomes an issue. So something to think about, and probably more for another talk. There are bindings for pull and select, which are some fairly complicated calls that let you wait on multiple different files or sockets at the same time. But not all of the structure construction that you would need to use those effectively have been added yet. So be aware, servers can be a little tricky with the bindings that are there. Now let's talk about UDP. For UDP, the process is that you're going to need to figure out the IP addresses of the host that you want to talk to. You create a socket. You bind that socket to an address with a port on your local system, and then you use send to and receive from to be able to send messages to individual addresses on other systems. And so you can readily send out a packet and just choose a different IP address each time, a different port. And similarly, you can receive packets from a range of places. So they're sort of multicast in several directions, and then at the end you close the port. So let's work through an example. You can create an address for the incoming port. In this example, I've done 99999. You need to create a datagram socket of the internet type, 0 for the flags. Once you've initialized that socket, there is a word that lets you make it non-blocking. This can be useful for dealing with that concurrency issue that I mentioned before. What that will do is that if you call receive from and there are no packets available, receive from will return immediately. Otherwise, it will sit there and wait indefinitely for a packet to come in. And then you take that socket and you bind it to that address, and you need to pass in the size. To read a packet, you simply create an address to receive the address of the income of where the packet came from. You also need to create a variable to store the length, and you need to initialize it to the size of the socket because, or sorry, of the address, because the API happens to expect that you may be dealing with buffers for addresses that are of different sizes. So you need to tell it how big yours is. Excuse me. You then call receive from, passing in the socket, a buffer to receive the message, a variable to receive the length. A variable specifying the length of the buffer that you've got, and a buffer for the address. You can actually leave out, if you don't care where the message comes from, you can pass in zeros for received and received length. And in this example, you can print out the packet. Sending works similarly. This is a little bit complex, but you can, here I've got an address for where to send the message to, and then this word takes a port and a host name. It puts the port into the outgoing address. It calls get host by name to parse out the IP address and stores that away into the outgoing address. And then it grabs the remainder of the text in the translation input buffer and sends that out as a packet to that address. So let's pop out here again to the device. So again, I've got a pre-baked example here with UDP. It's the same kind of code. It's actually structured with a little bit of help at the bottom. And this example, both of these two examples are actually available in the source base. I'm going to go ahead and load this example, and so this loads the code. And the way that I can use this is that if I want to just listen, I can just do this. I'm going to leave out the word here because here is just actually one other new feature for those following along is that I've improved the structure of the listings, but this word just sits there and pauses indefinitely, which is not a particularly great word. On the Linux version, because the way the console works, this is necessary to yield and pause, but on ESP32, the terminal or tasks continue to run in the background while you're sitting there at the prompt. So it's sufficient to just listen and the messages will come in. I will then go over to my local system and I will run, this is now on a Linux or Linux through Windows actually. And I will run the same program locally here, and I will go ahead and I will bind. I'll bind a different port just for fun, and then I will send a message to port 999 and I will pick the name of this device, which I need to go back and find the IP address of my ESP32, and oops, too much in the buffer, and we'll give ourselves a little space. I will paste that address here, and then I will send a message, hello there. Now I'm going to hold up this board because I'm far away from my router, so but this is actually useful because if I send this message, oh, that one didn't make it through. This is a good example of the fact that these can be unreliable. If you're close to the router, you're likely to get all of the packets. But if you're not close to the router, there is the danger you won't. Let me hold it up even higher. And that's not good. Okay. This is a good example of demo fail. We'll try it one more time. Okay, this is where I double check and say, did I? All right, I'm gonna cheat a little bit and use, so netcat is a useful Unix command that you can use to communicate over UDP or TCP, and it makes it convenient to type in a single line. I could do the same in forth, but I'm gonna, in the interest of seeing a packet make it to the other side, I'm going to use it here. So this will just send a series of packets, and let's, okay. I'm gonna call demo fail on this one. Unfortunately, this is what happens when I'm in a room that's far away from my my router. We can of course cheat and send a packet locally. Let's so if we send a packet to ourselves and on localhost, we will receive it right back in the same interface. You can actually send it either through that interface, or we should be able to send it to the IP address, the external interface. And actually, I'm not sure how well this will tolerate a space, so I'm gonna.
Yeah, should that be 86 rather than 68?
Hold on, let's see here. Oops. Did I flub the address? Is that the source of all my woes? Let's see.
Yeah, it could be.
Let me hold on. Let me scroll back up here. If I had the presence of mind to remember what the name of the, oops, this is the trouble with filling your input. You know what? Let's let's reboot and let's set up the connection fresh so that we get to see the address somewhere more recent in the buffer, and it is 86. Oh, okay. So let's go ahead and include, that might explain our demo fail. So let's go ahead and listen on that port. Let's go over here and let's try, so we need to open a port here, and maybe we'll get lucky and we'll get to Hold up the device, and no such luck.
You got to
All
say
right.
twice there.
Let's try it locally, and we'll. Ooh, that didn't work.
You got to say twice. Is that correct? And 9999 say.
Oh, that is not correct. Okay, that's wow. Okay, just infinite. Okay, let's one more time here. Well, yes, it's good. It's good that I got you all checking me here, because that's how we're going to spot. Yeah, that's probably okay. We're going to listen for the packets. We're going to come over here. We're going to do 999 say, and then we're going to do 192.168.86. Oops, 168. Let's see if we can type 86.247. Hello there. Hold up the device. No. Okay. All right. Let's do the local one, which I assure you it works when you have it when you're closer to the router. But there, for example, you'll notice that in this message it shows the inbound port there. I'm going to pivot over back to my slides. The one other thing you might have noticed, this visual editor. For those that are interested, you just do visual edit and then the file name. It's arrow keys and page up and page down to move. You can type and insert and delete. Control S to save, Control X to exit, and it will ask you at the end if you want to save. It's a terrible editor. It actually redraws the entire region that you're in each time, but it's a baby step in the direction of offering an actual visual editor, and so I figured I'd get it out there. Are there any questions?
Nice work, Brad.
Thank
May
you.
I,
Sure.
Brad, in one sentence, can you define what a socket is?
A file descriptor that represents a connection to another machine.
Okay, I'm happy with that. So it's a combination of data that describes a connection with a machine.
Yeah. Think of it the same way you would think of a file handle for opening a file to be able to read and write the file. It's a connection to let you read and write talking to another machine.
Thank you.
Yeah, Brad, thank you very much for that presentation. A lot to get through. So I think the thing to do is to work through your examples and see if I can recreate what you've just been demonstrating. Thanks very much.
Yeah, and please reach out by email if you run into issues. The apologies, I should have thought ahead that it'd be better to be far away or better to be closer to my router for this this demonstration. I tried it during some of the other talks and it was working reliably, but I think I'm just on the edge of proximity to it, and so it has high enough packet loss that it's an issue. So
no, that's cool. There's enough there to get going, I think, and whether it worked or not is a bonus. But yeah, that'll get us going, I think. And the next thing to do is for whoever's interested in it to do a few simple examples and expand on it.
all right, well, thank you. Back to you, Peter.
Well, fantastic. I think it's very clear, and we need to think about, Brad, you are very fast and on typing and showing us a lot of new information, but we are all very happy.
And the nice thing is we have the recording so we can see
Slow
them
down.
over and over again, slow down. Yeah. Great.
But also, Francois, a very good demonstration. Thank you very much, Francois, for your speech.
Thank you.
Sure.
It was a great meeting.
I
Fantastic.
appreciate that because porting forth code is a marginal activity that very few people indulge in these days.
Mm-hmm.
Most people assume ANSI standards on little endian architecture, Intel, and when you do not fit that profile, you're in trouble and bugs show up. And bugs are definitely not portable.
Brad, I need also to tell you every time of the day here in Brazil, near Sao Paulo, there is a guy who has always an ESP32 forth running on his desktop, and this is me. And I enjoy a lot, and I create examples for the group and experiments, and many people are using ESP32 forth and MECRISP. These are both, I told Ulrich, both of these forths have a lot of followers and people who are trying it.
Mm-hmm. Yeah, I'd agree with that. So I use my little ESP32 forth quite a lot, and I always have the glossary open at the same time, so I can get the flavor, because each forth is slightly different, isn't it? But there's an awful lot to explore in there, and so it'll be fun to do that over the coming months.
One other fun thing just to mention, I think it just occurred to me, I haven't mentioned it to this group, but I have a long-standing, been trying to get a version of the same engine to work on the web, and the link I just pasted there lets you interact with a copy running just in the browser of an engine that is relatively close to the one that runs on ESP32. So folks can check that out as well.
Hey Brad, there's a version for Windows, is there? I think
there are Linux and Windows versions as well.
Is it fairly close to the ESP32 forth code?
So the core is the same. The bindings are a little bit different, but like the bindings for sockets and terminal and things like that are similar. So
that might be handy to sort of prototype things with.
Yep.
Shall we stop recording now, Ulrich?
Yeah, I think that concludes our meeting today. So thank everyone for joining, and I will stop the recording. And here we go.